Okay. I think we're streaming. Let's see if Twitch Rogers that. Oh, you were smart. That is the healthy move.
I can't eat pizza anymore.
Really?
I'm to that point, really.
I mean, it is terrible for you. It's so bad for you.
Well, no, I mean, every meetup and everything that everybody wants to do now,
Yeah.
they just order pizza and it's like the de facto thing.
Yeah. You can get free pizza any day, any day of the week. It's definitely. In fact, I'm pretty sure we sponsor like a lot of meetups. A lot of like, look, we were thinking about doing a bot that would collect every single time someone tweeted about thanking Smart Logic for the pizza. It would just go through Twitter to find all the tweets referencing us and giving meetups to pizza. You're on Twitch right now. I went to Twitch and NASA's on the front.
I'm going to repurpose your plug here.
Yeah, go ahead. There should be. Okay, I am streaming, but we're not streaming about ElixirConf. We're streaming about artificial intelligence. Hello? Hello? They didn't talk back, so I don't know.
Guess one time?
It's Smart Logic Guest. Oh, you found it.
Thank you.
Veg.
Yeah.
Would you be worried about putting my veggie on top of my meat?
Why not?
Or just like eating a sandwich? The disapproval is strong. I'm gathering that that's not okay. I have to eat them separately like a mom frozen. My trainer was shaming me today for not eating enough. I was like, I'm gonna go eat a bunch of pizza right after this.
So, by chance, did you put this out on Solitaire?
I didn't. Will you?
I could probably put, yeah, I could put this on here. I did give it cleared for public viewing, so I could do that.
Appreciate it.
Yeah, absolutely.
Overfitting, you just post it on the meetup site. Either way.
Hey,
Whatever. There's more
welcome.
comfortable.
Yeah, it's yours, by the way.
I'm Pete. Pete
Justin, nice to meet you.
Okay.
James, Kevin, Alex, Dennis, nice to meet you guys. Please welcome to the meetup. Pizza. This is Dr. Bruce Dean.
Greetings.
Tonight.
How's it going?
We'll do introductions. Probably like another. Yeah, probably another 5 or 10 minutes. Let's settle in here. Hey, man, welcome back. Good to see you.
yeah, this is what happens. Everybody comes in.
Hello.
Hello.
Yep. So just buzz 323 and then hit call on the box in door, and then I'll be able to get. Yep. And then we're on the 3rd floor. All right. See you soon. Oh man, thanks. What you doing, man? How's your pizza?
Cool. I might go to
I need your help, man. I can't be here. Where are y'all coming from?
We're from UMBC.
Wicked. Welcome. Glad you can make it. Are you all comp sci students or?
Yeah. Yep.
Sweet. You're in the right place. This is gonna be super good. Help
You
yourselves.
can plug
There's
in
cheese
that
under there.
button.
If you're, you know.
Is there an
They
There's
did
actually
cheese.
more on the other side.
I like that.
That's why I did it, because
The vegetarians come out and they
normally
house
I
our
bring
cheese
bad
pizza.
electricity, I would plug too many
But only if they
things.
come out.
So I just carry that thing with me.
You're not vegetarian, are you?
Well, that's nice. That's good.
Container store. I think it's
You're vegan?
That's
10,
like
15 bucks.
a
Oh.
few weeks ago.
That's cool.
Oh, that's why you're not eating pizza anymore.
Maybe I'll take this over.
That's a much more serious reason
Over the top.
than like medicine. You know, like medical. Like if it was like a medical reason, it's just like something's wrong with your body. Because if you're a vegan, there's something wrong with your head. No, I'm playing. You're totally good. I'm joking. Huh?
You have a restroom close by?
Yeah. When you walk out the front, this office, it's just on your left.
Okay.
Yeah, it's right across from.
No.
I'm joking, Daniel. I actually think it's super noble and admirable. Gandhi was almost a vegan.
Almost.
Well, he was a vegetarian. I think he was a fruitarian for a while.
What year are you guys?
We're all seniors.
Oh, okay.
Actually, I'm a junior. Kind of.
Okay. All right. So on the down slope, they're ready to be out. You graduating in May? This May coming up. Okay.
Yeah, one more semester.
You had internships. You got anything
Can't
lined up?
wait.
Yeah.
Got anything lined up? Had any
Not yet.
internships or anything? Like,
I'm working at a place called Vectorworks.
okay. Cool. Is that in the Columbia area?
Yeah.
Okay. All right. Cool. What are you doing there?
UMBC.
That one's open. That one's open. You can pull chairs from outside if you want.
You think you're going to stay local, or do you think you're going to try to like Silicon Valley or
I have
Seattle or Austin or?
right now, as long as Vectorworks wants me there, I'll stay there.
Cool. What does Vectorworks do?
It's an architecture software company.
Okay.
Yeah.
You talking about like real architecture? Or-
Yeah, like
okay.
real architecture.
All right. Cool. I'm John, by the way. Nice to meet you.
Yo, Ankit. What it do?
I
Yeah,
work
you
with a
gotta
lot
hit-
of smart people.
You got to hit 323 call, and then I'll hit 9 on my pad once I get that.
Oh, where do you work?
A small defense contractor called Red Alpha.
What do you do?
Sounds. There he is. All right, come in.
Software engineering, software architecture. Yeah. Full stack, back end, high performance processing systems.
What language are you writing that in?
What is that?
What language are you writing that in?
Oh, right now it's nothing fancy, like just
Java.
straight JVM stuff. Yeah, you know, boring. Some Go, we sneak Go in there.
You sneak Go in there?
Sneak,
You know Johnny
I
Borsa?
sneak it in there.
Do you know Johnny Borsa?
Mm-mm.
He runs the Go meet up here.
Oh, really? Oh, yeah. That's what I was talking. Was it Dev Week?
Yeah, he taught me how to program like back in the day. Like
Oh, really?
Yeah, like 5 years ago, he taught me how to program Ruby.
Really?
Yeah,
Yeah,
that
he
was
just had to go meet up on last Saturday, I think.
He's brilliant. He's even
Yeah.
the one that inspired me to become a Vim user. Like now I.
Oh, really?
Yeah, 'cause I used to see him with like using Vim when he had like 5 panels and they'd all be doing shit. And I'm like,
Yeah.
what? So then now I do that.
Dude's off the chain.
Yeah.
I want to get to his meetup sometime. I
You should
think
go.
it was on Tuesday.
It's on Tuesday. It's at Under Armour.
Yeah. Okay.
Go is a good language to learn.
Yeah, Go is pretty awesome, man.
But if you're really smart, you pick up Elixir and come work here.
They call it Elixir.
Elixir. Hey, what's up, Mark? Hey, how you doing?
Hey, everybody.
Hey, how you doing?
Is that an empty chair?
Yeah, it's an empty chair for you, and we'll grab another one for this.
Trick hazards.
Hey,
Field loader. Some timeline. Those are the things.
So, there's beer on the way for everybody. It's fine. That there's water in that fridge, liquid water and club soda and stuff in that fridge. Please like make yourself at home. Me, Officina, soup, Officina. All right, so it's 7:13. I imagine we'll get a few more stragglers, but why don't we do a quick like round of names, where you're from, what the nature of your interest in AI is, and yeah, let's just do those, and then we'll bump into talk. So I'm Justice Epen. I am a full stack developer here at SmartLogic. We make web and mobile applications in Elixir on the back end, React on the front end, sometimes Ruby on Rails. That's my jam from way back. We do that kind of work for lots of different folks, from Sagamore to the Water Taxi to Annie Casey Foundation to McDonough High School. So we've got lots of clients. That's awesome. I am obsessed with artificial intelligence. If you've been to the group before, you probably know that. Like, I hope that the passion just like oozes out of me. I'm stoked about it from the technical side and from like the philosophical side, and I'd be more than happy to talk your ear off about that. But I won't do that tonight. So that's me, and we can do counterclockwise to give the new guys some time to get acquainted.
Yeah. Because last time, I remember like, you were sitting right here. I was like,
You were last. Now you're first.
John White, software engineering, software architect, graduated from Oregon State University years ago. I just like AI because I just think it's cool. I think where everything's going, I truly believe that it's beyond a fad, but I think every application is just changing the way that we develop. I know that every application in the future is going to have some type of deep learning, artificial intelligence, machine learning in it. So I'm just interested in it. It's just something cool to kind of geek out on, and something that I know that I have to learn and be relevant to continue to like function at a high level, I guess, professionally. So it's just where everything is going. So, and I just want to be around smart people that kind of geek out on it and just learn some stuff.
my name is Ankith. I am in a suit because I am skipping on my holiday party right now to be here.
Yeah.
I may have had a couple bourbons in me already. But
Oh no.
So I work as a quant for an investment firm here. I generally focus on hedge strategy, dealing with large portfolios, like a couple thousand positions, and optimization strategies that we can glean from them, which makes machine learning algorithms something that we have been looking into. I've implemented some for some simplistic things, but I'm always trying to figure out something that's more efficient and higher quality than what we're doing now. So that's kind of what brings me here.
My name is Patrice. I work for a company called DXC. Right now, I'm working on a project that's basically about the Internet of Things. And so basically, how do you manage these things? So are they up? Are they down? Are they healthy? Do they need maintenance? And so our perspective is to get artificial intelligence in there to actually find out, based on the amount of data feed that we get, one line or 126 lines of data. Where is the noise, or where is the out of bounds, so to speak? And so we're hoping that we can use artificial intelligence to give a predictive idea of either a failure or a requirement for maintenance. Pretty much it.
Thanks.
Hi everybody, my name is Bruce. Thanks Justice for having me over. I live out towards Frederick, Maryland, but I signed up. I joined this meetup when I first saw it. When I first saw it on the list of meetups, and I thought it was just a great idea to get people together locally to talk about, particularly machine learning and other software kind of stuff. I've been at NASA for 20 years. I pretty much went there right after I graduated. I have a PhD in physics. My dissertation work was in general relativity, but I've always been interested in software. In fact, I've been writing software since the first computers came out that I had access to, like the time like Sinclair. And then I had a Commodore VIC-20. So every generation of people that talks about their software experience, it's a little older, goes way back into stuff, right? Because I heard, guys talking about machine cards and punch tape and all that stuff, but for me, it was like the Commodore VIC-20 and a cassette drive. Store programs. Yeah, come in. So anyway, super psyched to be here. If you know me, you know that I'm basically obsessive compulsive disorder. No matter what I'm working on, I get really into it. Probably like you guys, you get super stoked about something and you learn more about it. Machine learning stuff. I can't speak for all of NASA, but I can say that there's a lot of stuff going on. There's a lot of interest in applying these techniques towards improving what we can say about science, what we can learn about what's around us. I'll talk about an engineering application for how I use it in my group. I'm a group leader at Goddard Space Flight Center, about 30 minutes down the road. And we'll talk more about that in a few minutes. But anyway, I'm just stoked to be here, and I like being around folks that are super interested in this kind of stuff. And I'm a quant guy on the side, just as a hobby.
Nice.
So I'll catch up with you.
All right.
So I'm Kevin. I'm an undergrad student at UMBC, studying computer science. I'm in intro to AI right now, although I just submitted my final project today, so it's a little bit.
You want a demo for us?
Oh no.
2 weeks from now, we would love to have you.
It might be better in 2 weeks.
Yeah, there you go. Take the time.
But my professor recommended coming to one of the prior meetups, and I enjoyed it, so I saw this one.
Great. Glad to have you. Thanks.
I'm Danielle. I am a grad student. I'm also a database developer at Dropout, and I took a machine learning course last year, and it kicked my butt. And I wanted to make sure I retained all the information I learned and meet other people that were interested in subjects as well.
Chris, worked at Smart Logic for about 9 months. Went to University of Delaware College for 4 years computer science. I guess that's what we were saying. I just kind of jumped in. Other than that, there's
Yes.
So
I'll do that.
yeah.
Sweet. You want to grab me one too? Thanks. It's free.
Please grab more.
I remember when I was in school, they usually charged me $5 at the door, or I was charging $5 at the door. Thank you.
It's my turn, I guess. Yeah, I'm Philip. Originally from Germany, just moved here. My background is originally in business and physics, so it's my first topic. But I switched fields, so I work now in medical imaging, in computer tomography, to be more specific, where machine learning is such a huge topic in other industries. It's uncharted territory for me, but
Glad to have you.
My name is James. I'm an undergraduate at UMBC, studying computer science now. I just think AI and machine learning is really interesting, and I want to learn more about it. So, Kevin told me about this, so come along with me.
My name's Alex, also an undergrad at UMBC. I'm just trying to explore the different areas of computer science and see what really interests me. And James told me about it, so I decided to come.
All
I'm Dennis. I'm an undergraduate at UMBC, senior, but I also work at Vectorworks. Right now, I'm working for the research plugin team. So I'm writing like external renderers for, or software that communicates to external renderers. But I'm also kind of interested in AI. I took a computer vision class last year, so part of my interest comes from there.
Yeah, please. You're actually the last one.
Sorry I'm late, that's my introduction, but I'm Sunil Prasad. I come here, I guess, maybe once in 2 months or something like that, every alternate month. This is a great platform. I work with a company with the federal agencies. I'm one of the vice presidents, and we are doing some stuff with the cloud transformation and microservices and stuff like that. So I'm glad to be here.
Great. Glad to have you, Sunil.
Thank you.
Great. Glad to have done those introductions. So glad for everyone that's here. I guess a quick point of administrative details. We're going to move to actually a weekly meeting schedule. The Hack Night's been really popular, and there's some traction with the idea that we want to put in work on a project as a group together, and it seems like we had a lot of interest in going from twice a month to just every week. So we're going to keep the speaker schedule the way it is. So first Thursday of every month, like today, we will try to have a speaker, and if we can't find a speaker, because they are extremely difficult to find, so if anyone wants to make introductions, please do that, because they're very difficult, and that's why we're so grateful to Dr. Dean for being here. So yeah, we'll continue doing speakers first Thursdays, and every other Thursday of the month we will have study hall here. We'll probably start a little bit earlier and end a little bit earlier. So I'm thinking instead of 7 to 8:30, we'll probably start at like 6 and go to 8. So everyone's more than welcome to come to work on a project, to just get some support on whatever you're working on. That's the way I'm looking at it. So if you have any questions, please ask us later on. Tonight, we've got a guest speaker, Dr. Bruce Dean. He's going to be telling us a little bit about how they use neural networks at NASA, and I'm just going to let you take it away because I'm super stoked to hear it.
Sure, thanks. Well, again, thanks again, Justice, for having me over. As I've mentioned, I'm super stoked. I like to be around smart people and get the opportunity to learn from other people as well. So I look forward to talking about what all you folks do and your interests as well. So as I mentioned, I've been at NASA for about 20 years. I started off in the optics branch. I have a PhD in physics and a master's in mathematics. And so when I came to NASA, I had a pretty good background in physical optics. I started off in the optical design group in the optics branch at Goddard Space Flight Center. And my first job was to essentially design camera systems for space satellites and space telescopes. And so I did that for quite a while. A couple of those made it to launch. Super interesting stuff if you're interested in cameras and lenses and optimizing images. It's a really great field to get into. Super high demand, as like machine learning. It's one of those areas where you can pretty much do what you want to do and have job no trouble. So started off in optical design, and then so after about a year or two of that, we realized in the optics branch that there's a pretty new technology that was emerging. It wasn't super new, but it was new in terms of what people were applying to imaging systems. And so the first part of this talk, I'll just describe you briefly, what wavefront sensing is, what wavefront sensing and control is, and how it works, just to kind of give you an idea and set the stage for why machine learning might be useful to apply in this application. I'll go to the first slide. I'll mention real quick, I can set up a download for these slides later. Whenever we present something to the public at NASA, we have to get public permission for public release. So these charts have been reviewed, and it's okay for me to get these to you guys. In fact, I will mention also Goddard Space Flight Center had a machine learning conference week before last, and maybe it was last week, but just recently, it's a free conference. You guys can come down. It doesn't cost anything. You just have to register in advance, so they get a head count. You can get your badges and everything. But they have it. They're going to start having it, I think, every year. So, or maybe more than once a year. But I'll stay in touch with Justice and let you guys know if there's one coming up. We just had one. So for next year, you should definitely come down to that. There's a lot more presentations on what other folks are doing at NASA. I can't speak for all of NASA. I can speak for how I'm using this in our group. But there's a much broader interest as well from other application areas. So in the application area that I wanted to talk to you guys about today, as I mentioned, I work in optical systems and wavefront sensing. So what does that mean? Well, essentially, as you guys know, when optical systems are performing well, when your phone cameras are working well, when your binoculars are working well, when your space telescopes are working well, you get great, beautiful images, right? By the way, I was really nervous about posting this image because I didn't want to get sued or get in trouble, right? So I did a lot of research and finally found the guy who took this picture. He was on Flickr, and I made sure I credited him and read the license agreement. But this kind of stuff, you got to be careful, right? And especially if you're representing government, you can kind of get in trouble or obligate yourself beyond what you should be doing. So a lot of little details go into these presentations that you got to be careful of. So anyway, great photo. I thought this was a nice illustration of an optical system that's working well. Now, when things aren't working well, as you guys might imagine, you've seen these classic target tests that show, say, a blurry image from an optical system that's not working well. There might be misalignments in the optical system. There might be errors in the way that the glass has been manufactured. There might be deformations. There might be thermal gradients that cause light to refract in a way that's not the way it's intended to in the design. And as a result, you get images that look kind of annoying and just aren't that great. And it happens in space telescopes. So when this happens in a space telescope, this is just a schematic of a model that we use for a project that I was working on. And what you can see in this model is that the light comes in from the top. I'm sorry I don't have light rays to kind of show, but light comes in from the top of the chart down towards the telescope, strikes the segmented mirror system, and then bounces up to the center and then back down a hole in the middle. So, but the point of this chart is just to say that between the time that this telescope is packaged into a satellite and launched and deployed, there's lots of little things that can go wrong in the system, right? There could be deformations, there could be things that move, that shift, that you can't anticipate, that you can't really know. It's sort of a stochastic random variable. You can't know in advance how this thing is really going to deploy. So as a result of that issue, we've designed what are called wavefront sensing systems, which let us look essentially at a star. So we can look at a star image, a point source, and with the image of the star that we collect on a detector, we can then process this image to tell us what is wrong in the optical system. And I'll show you what this means more specifically in a few minutes. But we look at images that are out of focus on purpose. Those are called diversity. It's a diversity function. So we look at images that are out of focus, and we can then process these images into an estimate of what is wrong with the system. And in fact, you guys might remember the Hubble Space Telescope. This is a great example, and this is why NASA got so interested in wavefront sensing to start with. So we launched the Space Telescope. What you see on the bottom are actually defocused images of a star. On the left is the actual, what it looked like through the system. On the right is a mathematical model of what we think it should look like. And so this is a pretty good match for telling us that we understand roughly what is wrong in the system. Now later on, after there was a lot of investigation, we went into the laboratories where this mirror was made, at Raytheon and PerkinElmer and others who actually work in this mirror. We found that there was a 2-micron edge error on this telescope mirror. But remember, Hubble's about 8 feet across. Primary mirror is about 8 feet across. And so at the very edge of this mirror, it missed the design requirement by 2 microns. But what that meant is that it seems kind of small. I mean, a micron is 10 to the minus 6 meter, right? It's pretty small. But at the edge of a telescope mirror, and because the wavelength of light is fairly short, this translated into a huge optical error called spherical aberration. And what had happened was Hugh Stansbury, the contractor, had actually been manufacturing other space telescopes for other agencies. But when they shifted to Hubble, there was some tooling that wasn't adjusted for the differences in design.
So what's the standard deviation that's allowed for something like this?
Yeah,
Like, what's your
there's
tolerance?
many different parameters here. Which
I mean, on that specific, like, what would be like
On that measure.
what's a tolerance?
Yeah, the standard deviation, the RMS wavefront error. Well, I'll say more about this in a minute for James Webb. I don't remember what the requirements were for Hubble, but the RMS
Or like
wavefront
at least
error,
like magnitude like 10 to the negative 9. Like what's the?
it's in the nanometer range.
So it's perfect. It needs to be perfect.
So our wavefront sensing error budget for James Webb Space Telescope is 15 to 20 nanometers sensing error. That's just the sensing error, right? So these are, we're getting down to the molecular level, right? And how these things have to go on. It's pretty tight tolerance. In fact, we met requirements back around 2005. I was involved in what's called TRL6, and that's where we had to convince an independent team that our telescope and the technology, this technology was working well enough to achieve requirements. And so we had to negotiate this number with an independent review team who actually wanted our money for their projects, right? So they had a good reason to shoot us down. But we convinced them that we could do it. We set up, and I'll show you some images from that setup. But we set up and we did experiments. We actually met the requirement. I believe it was like 1/8,000th of a human hair was the tolerance we had to meet. And we met the tolerance and we exceeded it by a factor of 50. So the technology works well. But long story short, this is phase retrieval was the sensing technique that was used to diagnose Hubble. Because listen, if you were in the control room and this telescope was launched and you saw these images, you would have no idea in the world what was happening, right? It could be anything. There could be, who knows, like a bird got stuck in there. You really don't know what happened, and you don't know what this came from. But there was a very careful, systematic amount of detective work, which later discovered that it was this 2-micron edge error. So long story short, the whole purpose of this chart is really just to illustrate this application of phase retrieval, of looking at a star image and then determining from that star image what could be wrong in the optical system or if everything is working properly. Okay, so this is a process called wavefront sensing, and one of the techniques that we use is called phase retrieval. Now later, using phase retrieval to diagnose and figure out what likely was wrong, this information was then used in a corrective module was built on CoStar, using the information that we learned from phase retrieval and other techniques. And then CoStar was built, launched, and post-fit astronauts actually went up to Hubble and installed CoStar to correct this optical error. And it worked. As you guys know, Hubble's been working fantastically ever since. But this is what happened eventually.
They might be putting a pair of glasses on the telescope.
Absolutely, yeah. It had spherical aberration, something that you would correct with optical lenses.
But they did it with software.
No, there was actually hardware.
Oh,
The software was used to tell us what type of lens to put up there, and then this lens was designed and retrofit.
So somebody had to go install it.
Somebody had to go, and you better get this right.
Yes.
You're going to launch an astronaut up there, risk their lives. You got to get this right. So
What year was this?
this was it was 19. I was in grad school. I don't remember the exact year. It was the early 90s. Anyway, I have a whole. You can talk about this forever. This is a great problem, by the way, because there was so much to learn about it to fix it. Now, all right. So Hubble is relatively simple. You guys may have heard about the James Webb Space Telescope. This is going to launch in like a couple of years. The control room, the main control room for the JWST is going to be right down the street here at the Space Telescope Science Institute here in Baltimore. And we have our whole team is going to be there. We're going to work shifts 24/7. Once the commissioning starts, it's going to take probably a month or two to align the segments. You can't really see it as well in this image, but this is an 18 segment here. Each one of these segments is about 1 meter across, 3 feet. So the overall aperture is close to 18 to 20 feet across. It's a large. If you don't know much about JWST, the bottom kite-shaped sort of structure you see at the bottom is to block the sun from overheating the telescope. This telescope looks back in the infrared, looks back in time by looking at redshifted light. And so it has to stay very, very cold. It's a very cold telescope, and if you let the sun hit it directly, it'll ruin the science. So the idea here, though, is that the telescope is so large we can't launch this in the conventional style rocket, so it's got to be folded up. I don't have pictures of how that folds up, but there's two big wings on the sides that fold in, and then the secondary mirror, which is sitting out in the front off the 3 spindle tripod, that folds down. There's a hinge at the very top. The top strut has a hinge, and this thing folds in to the center. So it's a deployable telescope. It has to be. It fits into an Atlas V rocket, the largest thing we have. And once it deploys, we expect all these little mirror segments to be out of alignment by almost millimeters, right? This could be a lot of launch vibrations. We get thermal gradients. This is near absolute zero, right? So there's going to be a lot of changes in the structural shape of this object that we then, so because of Hubble, the wisdom from Hubble is that, all right, we're going to build into this design a system that will allow us to make adjustments after it's launched. So we don't have to go up there and try to fix this thing, right? And the real problem is you can't go to this thing. This is an L2, which is L2 is the name of the orbit, and it's so far away that we just can't launch someone out there to fix it. It's a dangerous place to go, and it's too far away. So you can't go fix this thing once it's launched. So it has to be able to correct itself. Right? So it has to be able to sense and then adjust once it's in orbit. So that's the idea behind having a wavefront sensing control system to be able to adaptively update itself based on what we learned from facial retrieval and wavefront sensing. Does that make sense? I'm trying to make it kind of intuitive. That's the idea.
Does each of one of these honeycomb pieces, are they? I know there's like an optical mirror, like a ground-based mirror telescope that uses a series of motors underneath each disc.
Yes, absolutely.
And so that's what this is.
There's a set. Every one of these hexagons, there's 18 hexagons. It's a gold-plated surface. It's made of beryllium, and behind it, and it's very thin. This would be a hugely heavy telescope. This is a whole new technology. It's a very lightweighted mirror, which allows us to actually very subtly deform these segments to adjust their shape after launch. So it's a lightweighted mirror. There are actuators attached to the back of every segment that allow piston, tip, and tilt, and then slight radius or curvature control with every mirror. So we can slightly bend these things as well. Awesome. So I don't know if that answers your.
No, yeah, because I think that's the idea.
Yeah. So anyway, this is wavefront sensing. This is the James Webb Space Telescope. This is one of the technology areas that we're going to apply to. And another cool thing, application. I don't know if you guys have seen this. This is the Green Bank Radio Telescope. This is in Green Bank, West Virginia, a radio quiet zone. This is an observatory. It's the largest fully steerable radio telescope in the world, and so these things are amazing. They look at radio sources, so much longer wavelengths than we see optically. But nevertheless, they've made hugely important discoveries in science, and this is the largest in the world. So I came across a paper many years ago about some folks that were working on this, and they have to adjust the surface of this radio telescope is aluminum or some form of metal, and they adjust the shape of this. And I got the idea. I thought, well, I bet you we can do this because in optics. We're in the shorter wavelengths in visible light, but in the radio range, we're much longer, like millimeter wave stuff, right? So I got thinking, why can't we do phase retrieval on this, but in the radio band? And so it turns out they already had that idea. They were working on it, but they were calling it something else because there was a disconnect between what one field is doing and another field. And so I got in touch with these guys and I said, hey, look, I think we're doing something that might be able to help you guys, or at least maybe you can try it. And so they said, sure, come on out. So we did. We went out and they put us up in these dormitories. They fed us for a week, and we had a workshop, and we had a chance to apply this technology, and it worked great. So, for example, the focus of the telescope is at the point at which the 3 green lines emanate. And what you see in this image is a radio source that we used as an image. And from this image, we were able to do phase retrieval and determined to a pretty good degree of accuracy. Actually, it was much more accurate than anything else that had been tried at that point. But it allowed them to adjust the surface of this mirror or the dish to maximize contrast for science data. So that's huge because they actually had built a laser metrology system that goes around the base of the perimeter. If I had a laser I'd point to it, but it goes around the perimeter of this telescope in a much bigger circle. But they fire up the corners of this receiver, and then they make small adjustments based on that data. But it never really worked the way they wanted it to. So it was unfortunate that it didn't work. But they were working on this. We came along. We had this workshop, and now this is something that they can use for their telescope to improve their science, and it works really well. Actually, so another cool application. So anyway, all right, keep going. So how can machine learning? How can we use this? How can we do that here? Why would you even want to? Right? Right. Why would you want to do this? So, so I got thinking about this problem, and by the way, as you guys know, machine learning, artificial intelligence, this stuff's been around forever, right? We're in the summer, another summertime. There's been winters. We're coming out of a winter because of the great work that these guys, Geoff Hinton and others did, showed that you could do this backpropagation, and now we have GPUs and other things. But these techniques that I'm applying here and talking about here have been around for a long, long time. You guys know this. So with that said, remember that as far as a neural network goes, and let me just back up as well, and you guys know this, but in machine learning, what's called machine learning, there's lots of different people trying to define and wanting to be the authority on what that is and what it's called. But you guys know there's a lot, and girls, there's a lot of different stuff, a lot of different things in areas of machine learning that are quite different. Like there's new areas, like actually reinforcement learning is not even new. It's been around a long time too. But there's areas of reinforcement learning, there's applications of that, there's applications of convolutional networks, things that we wouldn't have thought about. And of course, now there's all the sentiment analysis and all the stuff that you guys could add to this list too, right? There's a lot of different areas of machine learning and things that are called machine learning. In this particular application, I'm looking at a neural network, and recall that from a certain perspective, if you really start writing the code and playing around with these neural networks, you understand that you're really just fitting a function. And so people get super worried and scared. I think that Skynet's going to take over, but we're just fitting functions. We can fit functions with anything we want, right? It turns out neural networks can pretty much fit any function. That's why they're so useful in many applications. So with that simple idea, if you had to just brute force your way into this problem and say, I'm going to bang my head against the wall until I can figure out something useful, you got to realize I'm just fitting a function. That's all I'm doing. I got features and I got labels. So what are the features and what are the labels? So to visualize how this works for this problem, start off with a simple optical system, or back to optics, right? So this is intended to convey what a perfect optical system would do. It's a single lens, but it's okay. You can regard an optical system as a single lens. If you're focusing light to a point, we're looking at a star image, you get a perfect circular image called an array function. And it doesn't matter what that's called. The point is that it's a nice symmetrical image. You can see from looking at it that it has a lot of symmetry, and that would tell you intuitively, if you were matching patterns, that that probably is something that's working well. On the other hand, if a mirror surface is warped, if it's stressed, if the temperature changes, if the mount of an optic doesn't flex and the optic does flex, you're going to get tension, you're going to get distortion, or any other kind of optomechanical thing you could think of would cause the system to perform less than ideal, right? So this is an aberrated image. The image is all messed up. It's unusable from a scientific perspective in terms of gathering data. It's not that useful to us. So you have these imperfections. No. So how do you deal with this in machine learning? You have to just imagine, and be with me for a minute, but imagine, so to really see where this comes from and see why it's useful, you have to just make a leap of faith and understand that there's every optical system, at least the kinds of things that we worry about, have what are called a pupil. Your eye has a pupil. Everybody knows about the pupil of the eye. Well, even space telescopes have a pupil. And the pupil is really just an image of the aperture stop, and that's where diffraction occurs. Remember, diffraction occurs in ocean waves and water waves. It's a wave phenomenon. It occurs in space telescopes. It occurs in our eyes. Every optical system has a pupil. Now, the pupil itself is where the data that we see in a camera plane or our retina, that's where the data comes from. It comes from a pupil, the transformer. Now, here's the biggest leap of faith you've got to make right here. It's just that the pupil consists of a number of things that we call aberrations. These are things like defocus, astigmatism, trefoil. There's all kinds of different aberrations that you could list out depending on how many you want to count up, right? But the lower order dominant aberrations are the types of things that do the most damage to an image. Now, it turns out that because we have control systems that correct these aberrations, we can think of these green bars. These are numerical values that we could apply to an actuator on a mirror that we would use to adjust that mirror back into shape, right? So how do we know how to do that? Before you launch any telescope, you go to a laboratory and you hook up these actuators to a mirror and you shine light on it and you like go crazy and you poke those things as many times as you have time for it and you have funding for it until you figure out exactly how much to poke to get a certain response. And you're mapping essentially what's called the influence function of the system. But the simplest idea, and the only thing that I really want you to take away from this is that you can view this image as coming from a mapping from these controlled degrees of freedom and these aberrations in the system. Okay? It's a pretty simple idea once you kind of get that much of it. And this diagram is just to illustrate and really just indicate that the pupil comes from this collection of coefficients, which could be degrees of freedom in the system, and then the image data itself comes from the pupil. Okay. So now the amazing thing happens, right? Why don't we just be bold here, right? Let's do something crazy, really crazy. Let's do something like just insane. Let's map these features over to a set of labels. We'll call it supervised learning. Right? You guys know about that. Supervised learning. Wow. Well, who would even try something like this? Well, I did, and a lot of other people. I mean, this is the kind of thing that we do in machine learning that you might not make these connections. And so the number one thing that when I'm talking about these things, and you guys are experts, have been working on this and write your own code and all this. But for anyone who is trying to figure out how to apply machine learning in their work, I just would like you to think about the kinds of mappings that you can come up with yourself, right? From one set to another that you might use to define a function that you calculate with a neural network. And that's pretty much it. You can do a lot of things with this idea, right? And you can map street addresses to divorce rate. You can do whatever you want to do, right? Crazy things. Every once in a while, you'll see some crazy mapping that I saw a mapping somewhere it cracked me up. It was someone mapped the divorce rate in Tennessee to riverboat deaths in Missouri. Some crazy thing like this, right?
It's similar to something that somebody did, and I had a discussion about this. And this is bad correlation is the way I call it. And it is like economics. No, it was cheddar cheese to divorce. Yeah. And I'm not kidding you. Someone argued this during a meeting, and I said, that's just bad correlation. And anybody who has either had cheddar cheese or been married know there's no.
So the point though is that there's a lot of applications where a mapping does make sense, and there are some applications where it really doesn't make sense, right? You can make sort of fake correlations, and that hurts the whole field and it hurts our reputation. But in some applications, you can make these mappings and they work. So in this case, when I talked about going to a laboratory and deforming a mirror and checking things out, and we built what's called a test bed. Ball Aerospace built it for NASA, and I spent several months out there in 2005. This is in Boulder, Colorado. Just to give you a sense of the scale, this is about 3 feet across. This was called the TBT, the Test Bed Telescope, and this was where we exercised a large range of what are called the conditioning algorithms that we're using for wavefront sensing control to help align this telescope. So, we're going to mess this thing up as much as we can on the ground. Right? You want to do as much damage as you can do before you launch, right? It's way cheaper to do on the ground, right? So we're gonna really challenge this thing, push these algorithms to the limits. We're gonna check the capture ranges. We're gonna do this stuff at an insane insanely obsessive level until we figured this out, and we did. So this is where we define the technology and tested things out.
It's 1/6 scale.
I think it is 1/6 or something like that. You can look it up. I can't remember the exact numbers. But these are small segments that were manufactured by a company like Tinsley. And underneath every one of these segments, you can see a little bit of the complexity of the actuator system, right? So this is what goes into how these actuators move.
Those actuators are actually warping every pane of the mirror.
Remember, most of them. So there's only really one actuator, a radius of curvature control in the center, that has an effect on the shape of the surface. The rest of the actuators give you tip, tilt, and piston degrees of freedom. Okay? So it's mostly positional type things, which do the most damage to the image. Right? If these segments are aligned to really the microscopic level, you won't produce a clear image. So piston and tilt, those types of things have to be right.
And your objective with the machine learning is to figure out what is the lens that you'll put on top of it to correct for the error?
Yeah, the goal of wavefront sensing and control is to look at a star image through this collection of segments, right? And then back out of that star image, where do these actuators have to go to correct the image?
In
It's
order
an
to
inverse problem.
So rather than putting the binoculars on the.
Oh, so this is an alternative to putting the glasses
The
on.
building in, we're going to just hedge our bets. We're going to assume that it's going to be screwed up when we launch,
Yeah.
and then we're going to be ready. Right?
And you want to use the positional actuators to correct for the errors. Okay. Okay.
So you're starting from the final image and correcting from there, or are you correcting?
We're starting from whatever state the telescope was aligned in.
Right.
And we collect light, and then we start there.
Before launch?
Well, we just finished a test program at Johnson Space Center last year called Otis, optical telescope stimulator. And what we did at Johnson was we set this thing up in a cryo chamber, we pumped all the air out like it's going to be in space, and then we tested it cryo. And so the overall quality of the mirrors was checked. The models were verified that produced what we intended to see. Okay? That was sort of a check. But the actual control of this thing to produce an image that we expect to produce real science is going to happen in one orbit after it's launched.
Well, so I don't want to take up too much time, but so in my head, if you're doing a supervised learning problem, your target, you know your error rate, right? So you can calibrate to your error rate. So why wouldn't you just calibrate your mirrors to your error rate before ever taking any single picture, basically?
Well, you could. I mean, you could try to do that, but you're still making a statistical. You might be off, right? What if you have a 2-signal event or a 3-signal event?
I'm thinking more like, have you ever taken your car to a bumpy road?
Time out. What is a 2-signal versus a 3-signal event?
That's a 95% probability versus 1 in 100 versus 1 in 20.
Okay.
Yeah, right. So you know about tail risk.
Yeah.
You got
That's my job.
You got something out there
Yeah.
you're not expecting. There's a lot of good questions, but in this, we really want to have a not close form, but we want to use if we know that an equation governs something, we're trying to estimate this thing, right? We're going to use that equation to solve it. We're not going to make a statistical estimate.
Right, okay.
We're actually
Yeah. So you might as well back out of the actual system versus some.
We're going to use a direct solve.
Yeah, okay, yeah. All right.
But I'll say more about that. But you'll see what I'm talking about. All right, so moving ahead. So, all right, good. So go from this, look at this. So these are actual images that were collected off of these segments. And so what you see is that there are a lot of aberrations present. And that's okay, we're expecting a level of aberration. But imagine now that you wanted to correct these aberrations. Wouldn't it be cool if you had a function that mapped directly from the images to the control space? The control space being the green bars. Wouldn't that be cool? That's what a neural network can do in this case. That's an application where we can use machine learning. We can map directly from the segment level images to control degrees of freedom through a neural network. Is that clear? I want it to be intuitive as it can be. We're just really making a function that maps.
Can you re-articulate what exactly these values are? Are these the actuators?
These are, you can think of these as degrees of freedom. They're really what are called optical aberrations, like defocus, astigmatism, spherical. The same kind of things that can go wrong in your own eyes that cause you to have eyeglasses can go wrong in space telescopes, right? So these are the actual coefficients. So if you go back to the image you were explaining to me, yeah, so see that green bar that points up the highest?
Yes.
The length of each bar corresponds to the numerical value. So longer means more. So whatever, that's like defocus, I think. That's the term for defocus. Defocus happens to be more in that instance. So,
Okay, so they're
this is actually the numerical magnitude of, it tells you what aberrations are present and how much.
So
these are all the sorry.
So it sounds like you're saying that the y-axis is the degree of the aberration.
That's right.
And the x-axis is
What is the type?
the type of that.
Yes.
Yeah.
Yeah.
So there's,
Yes.
I guess, what, 10 factors
In this case,
in image stabilization. Or
And you can always construct a set to be as big as you want. But for purposes of discussion, this is a 15-term set.
so like, are these like natural? Like, are these domains specific to optics, or are they like just quantitative parameters that you're defining?
The technical answer is that, which maybe is not the best answer, but the technical answer is that these are polynomials that we've constructed to be orthogonal over a hexagon.
Oh, okay, got you. So it's like a PCA with 10 terms.
That's right.
Okay.
Okay, and so just so I'm super clear, across the x-axis there actually is no relationship, like between one type of aberration and the next type of aberration.
No,
Or is
they're
there?
orthogonal.
They
That
are
means
linear.
they're linearly independent. That's right.
Okay, they are linear. Okay.
Yeah, good questions. Good questions. Yeah.
So where would you find test data for something like this?
You have to build something like this.
So, so that's it. It's just.
Well,
this
no,
is the
there's
only thing.
we use this in all kinds of different applications. This was specific to JWST, so we built a test bed to be domain specific, right? There's a unique set of problems with an 18-segment aperture that would warrant building an 18-segment aperture on the ground before you launch it into space. If you wanted to hedge your bets, you'd want to have as much experience as you can with something that looks a lot like what you're going to launch into space first, but in a lab before you can get to it. That's why we built this. All right. So I apologize. This is a long explanation, but I wanted this to be clear. All right.
I think this is what we've been dying to hear.
I hope this is good for you guys. This could be I don't
Yeah,
want it
it's
to be
great.
long, but I want it just to be clear. What is the application?
Take as much time as you
So now we get to into what you guys know. This already know really well. This is so. Well, so where do you start? Who knows, right? You just try something. Does it work or not? Who knows? So I just started with a naive architecture, and naive for me is a cat classifier, something like that, right? Something you would say yes or no with. What is in an image? But if you look at a cat classifier, I actually have a great set of charts that I have on this computer. I can relate this later. But all I did was I said, let's try a multi-layer perceptron, right? Let's do that. So how would you do this? You take an image. This image is 64 by 64 pixels. This comes from a model of an optical system that I calculated. Okay, so I calculated this image from a model, and then I'm going to send this every pixel individually. This is the architecture part. I'm sending every pixel. I'm assigning that to a point in the input layer. So pixel 1 all the way down to pixel n squared, n times n is 64, right? So I'm just sending every pixel of this image into the input layer, like you would for a cat image, something like that, right? That's all. That's the same idea. And then let's do something simple. Let's just use a single hidden layer, and I mapped every pixel to a node and an input layer, right? And as you guys know, you can send this to an output layer. Now the z's are the coefficients that you saw before, right? So I'm going to solve for those coefficients, right? I'm solving for those. This is a function. I'm going to solve for these coefficients. I'm not doing classification. What am I doing? Yeah, but what in the end? What am I getting out? How am I solving? It's not a.
Are you doing a correction on the image?
It's regression, right? It's a regression.
Yeah.
It's not a classification. A classification is more of a yes or no. So if I was doing classification, what would I use as?
You want values output back.
I want a numerical range, right?
Right. Yeah.
So I wouldn't use something like maybe a sigmoid. A sigmoid maps you
To a binary.
to a
that's yes or
binary
no.
probability, right?
Yeah.
0 or 1. Less than 50% might be a 0. Greater than 50% would be a 1. Or a sigmoid. We can talk more about that. But this is so I'm constructing a naive multi-layer perceptron architecture that maps pixels in the input layer to the coefficients in the output layer, right? And there's the coefficients, Z2 through Z15. I left Z1 out because it doesn't matter in this application. But this is the key idea that I just want to.
So if you're doing gradient descent on a series of polynomials, how are you getting one single gradient descent?
Oh,
Back
well,
propagation.
you do it in parallel, right? This is where
okay.
this is the matrix multiplication that you carry through.
All right.
And then the back propagation. Remember, everybody says back propagation, but all you're really doing with back propagation is calculating a numerical gradient. That's
Right.
the
Yeah.
only
It's
reason
just
you're
a
doing it.
series of.
That's all you're doing. It turns out that if you want a numerical gradient, if you want to be able to solve, so you guys that have had calculus, and most of you guys probably have, if you have calculus and you solve for a maximum or a minimum, that's really what we want in this. We want to find the weights that put this network in an extreme, right?
Yeah.
We have a loss function, an error metric, right? So I want to be able to tune these coefficients in the output layer to match an image, right, with an error function. I want that error to be a minimum. So I'm going to calculate a gradient of that function. That's all the back propagation is doing for us.
Right, but so if you're doing a back propagation, but each one of these input value or output layers is its own polynomial that you've defined, right? So then, based on whatever the orthogonal polynomials you're talking about, right?
Right.
So then, are you doing an individual back propagation
No.
against?
Well, remember, these aren't, the neural network knows nothing about polynomials. There's no polynomial calculation in this at all.
Oh, okay. No, I see.
I'm doing something crazy, right? I'm
Yeah.
mapping those pixels.
Yeah, I see what you're saying. I see what you're saying.
I'm going straight from those pixels in that pixel space to the Zernike coefficient. So, sorry, Zernike is a famous guy that came up with a basis set that we like. We use it a lot. So it's called a Zernike. That's why there's a Z in front of every number. Because you can construct different types of basis sets. The Zernikes are if you Google that, you can see what Zernikes are. But really, I don't want to complicate the discussion with it being any more than just numerical values that we attribute to errors in the system. Okay? So the image on the left, the far left, is the input. It's an aberrated system. It has some content that can be expressed in this basis set. And by training this network of these weights, I'm solving for these weights that minimize the loss function, right? And then I'm going to produce a set of weights that allow me to take any image and then perform generalization and to data that it hasn't seen before. That's a really important idea. Right? That's the biggest, most important thing about anything that I say today is this idea of generalization in the way I look at it.
So you get the loss function
Yeah.
by comparing the output layer to the values for the image that comes from the scope, the telescope that has no aberrations, right?
Yes, I think that's the correct way to say that. Yes. And I had to rethink, how the loss. So yeah, the loss in this case. Remember, when you define the error metric, you find a set of coefficients that, when perturbed, produces an image that is slightly different, and then you subtract those two and you try to minimize that difference. The output of that, once it's minimized truly, then would be a solution to the problem. And you kind of read both backwards again.
So you're saying it's kind of a guessing test to figure out what.
Oh no, it's not a guess. It's
Well,
an optimization, right?
Well, no,
Gradient
for,
descent.
for the output layer. I'm kind of wondering how you calculate the loss too. It's kind of confusing. You're saying like how a change in each one of those nodes changes your input.
Yes, I know how it back propagates. I know how those differences back propagate. And all I'm doing is now have a multi-dimensional space. In this case, it's 15-dimensional, right? And I'm going along every axis in this space that we can't visualize. I'm trying to find a minimum trying to find the coefficient that minimizes the function in that space. And that's essentially the output.
So if you're using, if this is all built for redshifted data though, does this only work at, well, not a fixed resolution, but a fixed distance? Like, don't you have to recalibrate based on how far away the, whatever entity you're looking at is?
No.
That kind of distances, that kind of
Yeah.
Well, I mean, because there's different, at various resolutions. Well, I want to say resolutions, but at various distances, wouldn't there be some lesser redshift closer to where you're looking at versus farther?
Yeah, you're making a leap there that we don't really care about in this problem because we don't really care where this data comes from. We don't care what kind of optical system it comes from. We're just saying that I can map.
Oh yeah, okay, yeah. Because you're looking at the end image anyway, so it doesn't matter.
Yeah.
Okay, yeah, I got you.
Well, let's keep going, and I'll show you how it kind of develops from here. So this is a naive architecture. We could try this, right? But why not? And then again, here's the output, right? These are the outputs that we would expect from the network, a set of coefficients that we talked about before, except I just flipped them onto the side and just to make the connection with what we.
So these are the same bars as we were looking on the last slide? Okay, I was going to ask that question, but I thought it was really stupid. Yeah. Because I was like,
straight to the story.
okay.
I forgot I didn't have the story, so I apologize.
Very cool. No,
All right,
there's
so
no dumb questions. There are no dumb
listen,
questions.
Here's what my professor, my advisor told me in college, that the dumbest question is the question you ask, right? Everybody, you guys have heard that. All right, so why not? All right, so we can use this multi-layer perceptron, convolutional neural networks, really because of how convolutional neural networks should work. You guys have played with these a bit. These have some really attractive properties that make them really ideal for this problem, and it's mainly because if you've written a facial recognition code before, and it's not too hard to do with the high-level libraries that we have like Keras. But if you'll write one of these codes up, even when using the examples, like even the MNIST, right, the handwriting that recognition database, play around with that, you can see that the tiny features in the images that we would want to care about and generalize later to a range of objects are what are called shift invariant. What this means is that the features of the types of features that form in an image, like the spike, see the spikes going at a diagonal through the center? Those types of structures, a convolutional network doesn't care where those are, right? We don't have to worry about centering anything. These are things that could be way off to the side and the network can still make sense of it. This convolutional aspect is really important and makes this a really good architecture for this problem. So I'll talk more about what happens in this case also. But the important thing about the convolutional network is that the early layers, if you played around with this, are used for feature extraction. Right? So you're after, so what's in there? What are the patterns that I care about? That occurs in these earlier layers of filters. And convolutional networks can be quite complicated and numerically intensive. You need GPUs and stuff, right? They're pretty, especially for image processing, they're bears to deal with. And then finally, right, at the end, we again, we flatten the network and essentially produce a set of coefficients that could be what we're after in the regression step. All right, so let's get to it. Let's train this network. I have a model because, we have models. We know how what's called Fourier optics. You essentially can take what we know about an optical system and calculate what the image would produce. That's called Fourier optics, and that's my specialty. And we can now take known sets of coefficients. We can generate these ourselves randomly from a random number generator. Like I can generate 15 random coefficients scaled to whatever level I want, and then I can transform those into the images through Fourier optics. Okay, that's a well-defined process. It's classical optics. That's what happens. Actually, a lens actually does that for you. A lens will do that for you. It'll take these aberrations in the pupil, and it will form an image for you. It will do that transformation automatically. It's called a Fourier transform, if you care to know. So I know you guys have heard that. So I generated the data set for the network. This is a great application. for machine learning, because remember, and you guys know this already, a lot of applications for machine learning are very data starved, right? They don't have data. And in fact, corporations will pay people to very carefully do stuff and make sure that supervised learning data sets are generated. People get paid to do this, right? Very meticulous work, because some applications don't have a lot of data. So you're kind of data starved. That's usually the limitation. In this application, if you have a 4A model that's any good, you have essentially an infinite amount of data. And that's, I think, what intrigued me about this application was because this was an application of machine learning where I was not data starved. In fact, it was the opposite. I could generate as much data as I want for this problem.
Was the process of creating aberrations on the telescope, was that automated?
Oh yeah, absolutely. Well, automated in the sense that I put it into a loop, and then I generated as many random realizations as I needed. Yeah, totally automated.
Just take pictures.
It didn't take pictures, but it calculates the data through a Fourier transform, and then I save like these little arrays that you see on the left. I save every one of those ones into a file. So yeah, you're right. It takes a picture of the data. So this is a great example, a great application for machine learning. So now we train the network in thousands of supervised learning examples. I think I used around, just if you're curious, when I was debugging things and making sure they worked right, I would generate 1,000. Computers, as you guys know, we can do things pretty quickly now, but I was limited. I had to keep these arrays pretty small. I didn't have I didn't have a GPU hooked up to this, thanks to, I'm going to probably vent a little bit here now, right? Apple doesn't like NVIDIA, right? So so NVIDIA drivers don't work, but you can get an eGPU to hook into your laptop, right? You guys tried to do that? To get that to work, it's actually a hack, right? It's like getting a Hackintosh. It's not really meant. And so
you guys can't just use like
you can do
Google Cloud GPUs or something?
Well, for some things, yeah, right? We have our own GPU clusters at work. We can't just go straight to the cloud. A lot of this stuff. Right?
We did a talk maybe 2 months ago about the new Google collaboration tools.
Colab's amazing, right?
It's incredible.
Yes. That's where you guys should be, right? That's what I would do.
Well, so if you weren't here today, we'd be doing a very, very bad demo in Colab.
So long story short, this stuff takes a while, and I'm like you guys, I'm impatient. I want to see if this is working. I don't want to come back in 2 days, right? So I want to constrain this problem to small images and small training set, just to see if it's even converging in the right direction. And you can make a lot of progress, right? You don't have to solve the whole problem. You can just constrain the problem a bit so you can get to an answer. So anyway, all right. So an example here's the data, and as usual, right? You break up the training data. Here's how you do it. As you guys know, you have a training set, a validation set, and a test set. That's how I same way. But what I ended up doing with this problem, this is where I started. I ended up going to K-fold cross validation. If you guys, this is really, I think, the best thing to do, because what you essentially do in this case. So let's say you start off with 80% of your data as your train set and your 20% is your test set, right? You never want to throw your training data use that as your test set, right? Because it makes no sense. A lot of people, unfortunately, your results are going to be fantastic, right? Because you got this great
until you do something new.
Until you do something new, because you overfit the data. So you always have a set of data that the network has never seen before. That's the test set. With K-fold cross-validation, it's super cool because, well, remember, if you only just divided this up once and you went with this, that would still be okay. It'd be better than you just definitely. The point is that you don't use the training set to test your network. You train you solve for your weights in the training set, and then you go to your test set and see how the network performs on out of sample data.
I'm sorry, so what is the training set?
The training set is some collection of image pairs and coefficient pairs that I've set aside. Then I've trained the network on
From
that
the
data.
original image or from something you had before that?
From the model data that I generated.
Okay.
I generated thousands of images.
Right, okay, so
And I'll take 80% of those or 90%, hold that up to the side for training.
Okay.
Then I'll take the other 10% and the network has never seen before.
Right.
When all the training's done, I'll feed in the test set and then see how it does. You'll see some examples of this in a second. Now, danger when doing that, as you guys know, danger of doing that is that, well, what happens if your test set had really unusual results that the network had never seen before, and that the weights of the network wouldn't have benefited from because it was so unusual, the data was so unusual that you might have had what are called outliers or unseen cases that, so the network just had never seen any data like that. So if you do k-fold cross-validation, you do essentially this, and watch, I'll step through. So you essentially, you train and test over every permutation of the data, right? And you do this k times until you've looked at, so the network has seen everything, and it's tested on everything. And what this does for you is it makes sure that your network has seen the whole range of data that you're throwing at it, and there's no outliers that it hasn't accounted for.
So the training set is what you're saying is cumulative because it would have seen all the data at some point, right?
But
Each one of these test and training scenarios is kept separate from the other.
Okay.
There's no wisdom that's learned.
So there's no
Yeah.
pay it forward.
There's no pay it forward.
But then, does the order still matter in your, so whatever the weight matrix is at the end that you get out of this, it matters what order this happens in, right?
Not in this problem. Not in this
Sure.
application.
If you consider the even distribution.
Because if you get a stress scenario at the first scenario, then your train set will probably mostly be rejected or edge cases or whatever of that initial set, right?
Yeah, the position of that particular data, the stressor, right, the one that is out of
Yeah,
sample,
the Six Sigma.
Six Sigma
Yeah.
one. The position of that one in the data set really has no meaning because if you set up in a lot of the default software platforms nowadays, automatically shuffle the data sets for you. They automatically do this. They randomize it in terms of the ordering, and that's for a reason. They don't want there to be any sort of cardinal ordering to the data, and they don't want the weights to reflect that. So in most applications, unless there's a reason to preserve, unless the ordering is important, like say with an RNN or an LSTM, like a temporal thing,
Right, yeah.
that's different.
Okay.
But you can still do k-fold cross-validation with the recurrent neural network.
And this set picks up the sensitivity of the edge cases if they were the like, if something was if the actual data was similar to the Six Sigma case, it would still register that accordingly to the Six Sigma case. Like it would recognize that.
Yeah, I haven't done that myself, but it's supposed to. There's supposed to be a well-defined technique for feeding recurrent neural networks temporally ordered data and still do k-fold cross-validation.
That's great because like the stuff I've worked on, it doesn't. It's hard to.
It's
get
supposed.
that to happen.
You would want to know that. I mean, for you, in your case, I would want to have that fact.
Yeah.
So
That's really cool.
Because you said they're all independent, therefore order doesn't matter.
That's right.
What is the value, or how do you take the cumulative, independent nature of all these tests to give it some benefit that you ran all these tests?
That's the neural network.
You're going to see. You're going to see.
Okay.
It's this idea of
magic.
It's this idea of generalization.
The magic weight matrix.
It's this idea of generalization that is really what you get at. And I'll show you why that's important.
We're about one step down from source here. So.
Okay, so all right, this is just tools to trade and how you might apply this network to this data set. Okay, so now we've gotten through the standard. We've gotten through how you divide the data, k-fold cross-validation, another technique, and now we're going to get to your question. Right? Why is this even? Why in the world does this work? Why does it work, and why do we care? It's what's really important here is that when you look at this collection of images, your brain is automatically trying to put together patterns. Right? You're seeing patterns that exist in the data. There's very sharp and strong patterns like snowflakes or whatever. You see something in these images that are striking. These are every one of these images varies by quite a bit, but in such a way that you can really see a pattern here. So what we're interested in, like our own minds and our brains can see this pattern quickly, and this is the kind of application where neural networks can to excel. It's because of this idea of a spatial, in this case, a spatial pattern, in your case, temporal patterns that are important, right? But in our case, we care about spatial patterns. And spatial patterns don't, the weights that would predict a spatial pattern don't depend on the order in which they are presented to the network to train it. Okay? There's no meaning in that ordering. There's no cardinal meaning in that ordering. But in this application, it's the ability of the network to generalize that is really important. Because, well, we're going to see exactly in a minute what happens, but it's this idea of generalization to operate on data that it's never seen before. Okay? And I'm going to give you guys an answer to a really tough question that someone's going to ask you someday, if they haven't already, about, why don't we just do this? And I'm going to tell you why you don't do that. But we'll get there in a second. So, back to these patterns. Turns out that if you wanted to, if you wanted a really cool job that was kind of a mix between optical design and working on cars, you could get a job like this. It's called star testing telescope. You can go work in an optical shop in Arizona or Rochester or any of these manufacturing places that have these dudes that can look at images through a telescope with their eye or a camera system, and they can tell you to a high degree of accuracy what in the world is going on because they're trained. It's a skill. It's a vocation almost. I'm telling you, there's dudes that do this. And in fact, telescopes that were made in the early days, Copernicus, Galileo, Newton, these guys were doing this. They were looking at star images through their lenses, and they were polishing, changing stuff, and trying to get that thing as symmetrical as possible because they knew intuitively that a symmetrical star image meant that their optics were performing well, right? So a really good optician that is skilled in star testing will look at an image like this example. He'll see a triangular star, and he'll know, for example, that that's due to a pinched optic in this situation. And not only that, he'll tell you where it's pinched, right? And if you do face retrieval long enough, like I've done, I can look at images myself and tell you for the most part what's in it, right? Face retrieval is really just a way for quantifying the star test. But listen, this is a skill. It's like a vocation. People do this, and people will always do this because we're hands-on.
Has there been any proof of the symmetric sort of intuition that you were describing earlier?
Absolutely, yes. Fourier optics. We know what the models predict. We know what's in the models. We understand the mathematics behind classical optics, right? We understand how optical systems form. This goes way back into 1920s, right? Classical physics. These guys were Rutherford, Sommerfeld. These guys worked out all these details, and then later, as technology developed through the years, into the 40s and 50s, optical engineering started to emerge as a field because people realized that they could apply these techniques to build systems that did the right thing. The idea is that you can calculate and understand what goes into producing an optical image is well understood. I mean, Maxwell's equations, well understood for a long time. He published that stuff in the 1800s, right? Now, it's taken many years to understand the full implications of the discoveries that were made, right? But those are things that are well understood in the sense that the physics is understood. Okay? It doesn't mean that there's not problems still to solve, and there's lots of work still to do to develop the state of the art. But these are problems that are well known. So, and the reason I like this slide is because it emphasizes that humans do this, right? So the neural network can generalize to these patterns, and so that's what humans do already in this field of star testing. So, and I would even say, yet again, another area where machines are stealing our jobs, right?
He's going to lose his job. I
lost my job. I got it. That network stole my job. All right. So the important thing, one of the important things, right? It's one thing to generalize. It's one thing to solve these coefficients and say something about these images, right? But when we really launch a telescope, we're going to have detectors that are going to be subject to noise, right? Everybody has had, collected images. If you played around with digital photography, you guys can produce images that if you have, if you don't have enough light, things look grainy, right? If you have a faint image, you don't have, the camera has a hard time producing a high contrast scene. And the same idea applies here. You can have not enough light, or it's photon starved, and so what you get is that the image that you're collecting is kind of at the level of the noise in the detector. Now, all detectors produce noise, right, just from their operation. There's something called dark current. So faint light, you get weak noise. If you actually turn a camera off and still measure the signal, you'll get something. It looks like that speckle. It's dark current, right? There's actually, these are quantum devices that, current flows at a microscopic level through these detectors. And what you want is your image to be at a completely different level of signal than the background level of the detector. So what happens is that when we have faint light, the noise produced by the natural operation of the detector can compete with the image itself. And so what I'm showing you from left to right is how you guys have heard the signal to noise ratio, right? The signal is the object we're imaging. The noise is the background that we don't want. So as the signal to noise increases, we get images that are closer to being what we expect to see or want to see. Now, one of the questions that I wanted to answer in this little project was, how well does the neural network do when there's noise that it hasn't seen before? Okay, so I can train the network on perfect data, clean data, no noise, no detector, and now I'm going to be cruel and screw this thing up. I'm going to add noise to the data and demand the network still do the same job. And then what's it going to do? And how far is it going to be off from what it should be telling me? This is an important question, because if you were going to use this in real life, in a real space telescope, where you're on the chopping block, right? You want this thing to work.
So you're adding in testing, you're adding the noise on purpose and then determining your
Absolutely.
threshold.
Yep.
Okay.
You got to probe the boundaries of stuff. This is the scientific method. You got to break stuff, right? Before you ever get the stuff to work, you got to break it. You got to try to break it. So this is trying to break it and understand what are the limitations given the noise that we know we're going to have. We have terms for this stuff in the error budgets of our telescopes. We know there's going to be noise. We know there's going to be cases that are less than ideal. And you better be ready for that, right? Or you're going to be sitting in front of Congress, right? You're going to be asking questions, answering questions in front of Congress. So you got to have this ready. How's it work? All right, so this is a busy chart. You guys have a laser. I almost hit a laser.
No.
Let me just point to the top. The top is the data. Let's go through this. The very top is, this is data that the network has never seen, okay? And then I was cruel. I added a ton of noise to it.
Wow.
Okay? I just said, all right, deal with it, network. What are you going to do? So what do you see in the very top row is, not only has the network never seen this data, so it's out of sample, but I threw a bunch of noise on top of it. So I trained the network first. I gave it data it's never seen. And on top of that, I gave it noise that it has no idea what it is. And I asked it what the answer is. What you see in the middle row is the prediction. So, and more succinctly, in the third row, in the green bars are what I know is in the model. Okay? And the red bars are what the network thinks is in the model based on the data. So these are the predictions from the network. Okay?
1,000?
Huh?
Your data set was 1,000?
Yeah, it could have been 1,000 or so images, but these are just showing like representative examples, 5 or so.
And when you get the correct values for the coefficients, how are you getting those correct values? Are you running them through the neural network that you showed, the naive implementation that you showed?
No. The correct values are known to me.
How do you?
I generate them.
Oh, okay, you're generating the noise using. Okay.
No, but the green bars are what I'm generating from the model that calculates the image. Then I add the noise later.
So the green are the pre-noise and the red are the post-noise.
Yes.
And the red is the approximation based on the post-noise.
And the red is what the neural network thinks is in the noisy data.
Yeah.
Yeah. Thank you. So, as we have
You found a laser?
as we have pointed to earlier,
Wow. Good work.
nice. So
Thanks,
so,
Chris.
So on the left here, so the green bars are the known, the red are what the network thinks is in the data. Okay. And now, on the bottom, I'm going to step through this as the noise decreases from left to right. So right in here, I can tell you right now that on average, after running 1,000 or so cases, on average, the error is 77 nanometers. And this number will become more meaningful as we talk a little bit more about the results. But don't get too hung up on the number. The point is that it's decreasing. And you'll see, and so the span of this is the error bar. This is how big the error is on the estimate. Okay? So as I go through, and so now look what happened. I'm going to go back. Now the noise dropped. So this is the signal to noise ratio. So as this number gets larger, the signal is increasing relative to the noise. Okay? And the error begins to drop. So the network now can start to tease out a little better what's happening. As I keep going and get down to where the noise is even smaller, we converge to around 30 or so nanometers. And you can tell from the images here, just from the 5 random examples that I pulled out of the out-of-sample data, you can see that it's not perfect. There's still 28 nanometers of error, but on average, the coefficients look like the known cases, right? They're not too far off. So that's
go back like 4 or 5 steps.
Yeah, because you're
One of
changing the
them was-
data, aren't you? I mean, you're changing the amount of noise of what you took as your data.
No, the data never had any noise to start with.
No, but you're removing the noise.
I'm adding less noise.
Thank you.
Yes.
Adding less noise.
Can you go back to the first one?
Yes.
You're just seeing how the model works. The model works with different controls, right?
Yes.
Why?
So robustness.
Yeah.
Yeah.
So the
it's-
disparity
and-
is
Yeah,
small.
but it's like the next
Yeah,
step,
some of the
it's just
this is why you have to look at a large sample, because some of the actual aberrations, because of the patterns that exist, are easy. They're not affected a lot by the noise, right? They're just not.
So what we
But some
can,
of them are.
So what we can take from this is at about the 400 level from an eyeball test, you get pretty good results. Anything between 200 and 400 is not reliable.
Yeah, the network starts to be able to
Figure it out.
generalize reasonably well and not really even being sensitive to noise anymore.
Right.
Okay? I think that's kind of remarkable.
Is that SBR point or what?
The SBR is technically at NASA it's called signal to background ratio.
Okay.
Signal to noise ratio, signal to background ratio, they're sort of synonymous. This particular number, signal to background ratio, I'm using this number because one of our contractors
So it's like an industry
prefers-
standard slope.
Yeah,
Okay.
well, it's not industry standard, but they prefer to communicate in this scale. So I've used it for other projects, and that's why you can actually convert this to decibels. That's a way really that most scientists would
Because
communicate
it's
this.
logarithmic.
Yeah.
Okay.
But a couple of things on this chart, this series of charts that are worth pointing out. So as we go back, look, see this, the loss versus the number of training epochs? Anybody that has trained their own network knows that you want to look at the loss, which is the error metric, right? Between the training data and the known value, and then the cyan or bluish looking line is the loss versus for the number of epochs for the out of sample data. And if you're using something like Keras, you can plot these things during the training or after the training is done and get a look at how well. So these are very
Is that what
important.
you're using?
Yeah, I did. I used Keras for this. This is a diagnostic that helped you understand how the network is performing.
Does everyone know what Keras is?
You don't know what Keras is?
Do you want to give a quick?
Well, it's fantastic. It's a great high-level library for prototyping quickly how a neural network in a given application will perform. And pretty powerful. There's a guy, Francis Jolet, I think his name. He's on Twitter. He's the guy who authored Keras. It sits on top of TensorFlow. If you guys, everybody's heard.
And
TensorFlow.
lots of other modeling libraries.
Yeah, TensorFlow is kind of it's Google's foundation.
Everyone knows TensorFlow. Okay. So
You don't know
Keras
what
is
it
the
is.
layer on top.
Yeah, Keras is a real high level set of knobs that lets you set up the networks.
And I guess my point in exploring that is that it's the same tool that everybody uses with their learning.
A lot of people use it.
Yeah, it's not like you don't have some, like ivory tower library that none of us have ever heard of. It's like Keras is like what we learned.
Now, when I first was learning how to do this stuff, I wrote everything by scratch. I did it kind of the old way and wrote out the matrix multiplications by scratch. I did all the back propagations by scratch. That's a useful exercise just so you know what's happening.
There's this idea that at any moment government is like 10 years ahead of private industry in terms of technology. Is that true?
Who knows?
Would you? What do you mean? Who knows? You're at NASA. You would know.
I have to ask a neural network. I don't know.
He's not willing to confirm nor deny. Okay.
Wait, so
you got to expect that answer from me, right?
Let's put it this way: is industry really launching that many satellites compared to government?
Well, on December 3rd of this year, SpaceX dropped the CRS-16.
So,
all right.
Oh, actually, okay. So a little bit of a digression.
The only thing I would suggest to you guys is that don't be paranoid, right? NASA is the most NASA is the most open agency there is, right?
I carry my phone.
We are compared to most of them.
That's what you want to do. You want to be open. You want to be able to talk about it.
But
That's what I'm here talking to you.
Across the street from you guys is NSA, which is the exact
No, they're
opposite.
not even across the street. They're at 132. That's Fort Meade, right? So they're not even across the street.
They're not that close. But no,
Take a bullet to get the spark gate, okay?
When you guys think of like SpaceX, like do you see it in the competition, or are you inspired?
Personally, I can't speak for NASA. I'm not a spokesperson for NASA.
Person.
Nice.
Whatever.
No lawyers.
Twitch, you saying?
You're streaming on Twitch.
Twitch. I'm not a spokesperson for NASA.
Uh-huh.
My opinion is that their work is fantastic. I think it's great. I love space technology I just think it's cool, right? I don't feel threatened by it. I think NASA can learn from it. I think we can all learn, honestly.
Amen.
Why not?
Cool.
Why not?
That's a bit come back to this.
Yeah, back to the president. Sorry.
So I've used TensorFlow, but I haven't used Keras. So is that like a hyperparameter tuning? Is that what Keras is?
We'll get to that.
It's like just one. It's like a very thin layer.
You still have to tune hyperparameters.
Okay.
But you can use AutoML. Is that the new library from Google to do automated hyperparameter tuning?
Yeah, AutoML's out. I started messing with it like a month or two ago, and the documentation was
It's beta.
really sparse.
Yeah,
And
it's a beta.
I think it's better now, the documentation. It can take a long, long time to run for you. I'd like to have a little more interactivity in what I'm doing. And AutoML will even tell you, if you go look at their GitHub site or install the package, Python or whatever, they'll tell you that it's for someone who really doesn't know anything about machine learning that wants to get something working in an optimal way. Now, I think it has a place. I think that in the end, if you want to, so there's a whole other idea that goes into even understanding why AutoML is important. And it's because these networks don't work that great out of the box. And I'm going to show you exactly that problem here. Just a slide or two. Okay? I'm going to show you why the hyperparameter tuning is important. So, keeping going here. So this is kind of cool. You gotta try to break the system to understand the limitations. So when you add noise, it affects the results as you would expect. But what I was trying to get at in this slide was that look at this little diagnostic guy here. Because I'm going to come back to this. Looking at the error of the network as it's training. So the training progress is really on the x-axis. That's what the epochs are. Is training progress. And I'm looking at that training progress. I'm looking at the lines for the training data error, and I'm looking for the line for the out of sample error. And I'm looking at how those compare to each other, and that's an important diagnostic that we can say more about. So let's get through the couple more charts. Look how so what you should see here is that look how the test error decreases as the network training evolves, right? And so that you kind of expect that in this case because the noise is decreasing also. So they start to coincide. All right? So now we can understand now we can talk about performance. So why bother with the network? Why bother with the network if we're not going to care about how well it performs, right? We got to think about this stuff. Otherwise, we're wasting our time. First case, underfitting. This is true in any application. You guys know this. If you underfit, you're not catching the signal, and that occurred in the first case. What this means is that network, there was so much noise there that the network couldn't tease out, and the network was not able to generalize. It was not able to generalize and see what the underlying aberrations were in the system because of the noise. It was degrading. And this is a very intuitive application for helping see what this underfitting means, right? What we really like is the optimal case. That's kind of what we got to towards the end. We got to a case where there was a balance between the error and the noise, and this is the case that gives you the maximum generalization. The generalization is what we care about. That's for generalization. Now this case, everyone talks about this case. This is overfitting. And that's exactly what it is.
Can you give a different definition just to say overfit or what you mean by that?
This is why I'm looking forward to this chart.
Okay.
So maybe this will be helpful for you, maybe it won't. But when in my work, we constantly challenge each other. We have a lot of smart people in my group, constantly challenging whatever we're throwing out there, right? So one of the people in my group said, well, why don't I just, you only have so many different types of things that can exist in the image plane, and you've only got so many permutations on the aberration coefficients. Why can't you just essentially create a lookup table that has memorized everything about the network?
Yeah.
And because there's enough weights and there's enough capacity. Capacity is the number of weights. The memory of the network is enough to do that for a very low-dimensional set. And I thought, man, that's a great question. Why in the world am I worried about this network? I don't want to do all this if I can just make a lookup table. Everybody knows what a lookup table is, right? That means I would essentially just take the image, find where it is in the row of the table, and then look off to the column and find out what the aberrations are.
But it's only for known knowns, right?
Well, that's only if you're guaranteed to never see anything outside that table.
Right. Yeah. Yeah.
And that's why the generalization is
Or
important.
known knowns.
That's right. So another word for overfitting is memorization.
Thank you.
So
Does that help?
Yes.
To me, that's a really great way to look at the problem.
So does the k-folds method all but guarantee you get optimal, or do you still have to stress test it to determine whether it's optimal?
No, you still should stress test it. Definitely should stress test it. The k-fold, so the idea of the k-fold is a little bit tangential to what I'm trying to get at here. And the point of using the k-fold optimization, in my view at least, is to when you're kind of designing the network from a top-level perspective, in terms of the number of nodes, the layers, and some of the hyperparameters that you care about, that you want to tune to get the best performance. The k-fold segmentation helps in those stages. So because it helps, what you want to see in the k-fold case is you want to see the errors in the different segmentations roughly the same.
Right.
You don't want to see one part of the data work a lot differently than the other part of the data.
So you want consistency.
You want consistency across the data set.
Right. Okay.
So that's more why that idea is important.
Gotcha.
The
Okay,
way
so then
now.
you still trust. Okay, I see. Yeah. Okay.
Right. So this overfitting idea is, I think this is a nice way to look at it. You essentially have memorized all the data, and as you all know, what happens when you go off the next data point? What's going to happen when you memorize something?
No.
You can't generalize. It doesn't know. You're going to get like a random number, probably, right? The network has no generalization ability at all. You can't predict beyond this curve what's going to happen because you've memorized everything. There's no generalization capability. And this is one of the key points behind any application of neural networks, right? Is that generalization is super important. Our ability to generalize is paramount. That's the premier. That's what we want. That's why we work so hard at developing our hyperparameters, our network, our architectures, optimizations. Everything is geared towards generalization. Super important. This is the enemy of generalization, memorization, right? So that's, to me, I think the best way to see that.
you think the results would have gotten better if your base set was whatever magnitude larger?
You mean the training set?
Yep.
Who's the diminishing?
No, I do think there's sort of a plateau that you reach,
Okay.
and I don't fully understand the all aspects to that. There's a lot more work I think that could be done. I think the biggest that I trained this application on was around 10,000 or so.
Okay.
But at the time that I even did that, I wasn't including anything big. Right? I only just wanted to see roughly how things would vary. Now, if I was building this for a real system that I'm going to really launch or do something with, then I'm probably going to do some really.
Yep.
This is only just to map out how things are behaving. This is more how business works. You only want to kind of map the bound of how get a sense of what's going on. Right?
It seems like the intuitive answer is that you need more features to look at. Because right now you're just looking at images, so X number, like it doesn't really matter how many more images, like even as a human being, you wouldn't make that much of a difference. But if you had another angle of the image, like some other type of data about what you're looking at, then
there's a lot of features that you can build in. I just want to keep it simple. So
Yeah.
So you got to start somewhere, right? So moving along. So hyperparameters, right? We talked about that a little bit. So we going back to our naive architecture, right? There's a lot of things you can do here. There's many choices you guys, as you all know, that you can make, right? You can tune the number of layers. You can add more. Here you get two hidden layers. You can change the number of nodes in each layer, right? Why not, right? You can change that. You can add dropout. Remember dropout? You guys know what dropout is? It's to keep you from overfitting, right? So what you do when you initialize the network, you're going to go ahead and drop out some number of neurons. You're going to drop them out of the optimization.
Below some threshold, it just knocks it out.
Yeah. This is a hugely important parameter in every network that I've worked with, is your dropout.
So what function, so you said you weren't using a sigmoid, but what function, like are you using that hard pass one that's like the
I'll show you.
elbow?
I'll show you.
Okay.
I use them all. To me, nothing is out of bounds. You got to try everything. So the dropout, you can change that. And so when I say dropout, it's the percent that will be thrown out randomly. So if I say if the dropout is 1%, then 1% of the neurons will be withheld from the training, okay, to see how it performs. And so what you might look at then is the loss function as a percentage of the number of neurons that are contributing or not contributing. You can kind of see an optimal point, and I'll show you guys that in a minute.
So just so I'm clear, because we were talking about earlier about using like AutoML to tune hyperparameters, that kind of thing. And when we're talking about the hyperparameters, we're talking about to some degree like the this whole architecture right here. So I guess my curiosity is, are you guys doing anything like that at NASA prior to AutoML being a thing? Were you doing any like sort of like you actually in your abstract you mentioned genetic algorithms, so that's
absolutely
you're getting there.
Okay. Yeah, you have to worry about hyperparameter. Remember, why are we even here? Why do we get out of bed this morning? It's because we care about generalization.
And is it all in Python?
Huh?
Is it all in Python?
I use Python. I use Python because you prototype quickly.
Okay, you don't have like a NASA programming language or something.
There is no secret language.
I just feel like I'm looking for the conspiracy here. I'm looking for the conspiracy. I'm really just trying to shut them down. Well, no, I was because when you're watching, like I was watching the space shuttle launch the other day, and I was like, there are people that still believe in like flat Earth, and I'm like watching a rocket deconstruct like in orbit.
I saw something on Reddit yesterday. It was like, so do the people who believe in flat Earth also believe in flat Mars? Because you can see Mars. Like, do they believe in that too, or is it just us?
They're just getting it's getting the plane.
We're the only thing.
You guys crack me up. All right. So dropout. We can vary the number of neurons that we're using. We can also change the activation functions, right? And I'm just going to draw a cartoon here. The first one on the left is ReLU, right? The second one is sigmoid. The third one is linear. I just threw sigmoid again on the right. But there's a whole bunch. If you look at types of activation functions that people come up with, or have come up with, it's a large set. Even if you go look at the Keras documentation or the PyTorch documentation or whatever you're using, Piano, there's a whole bunch of activation functions. They make it easy for you to have access to. Because what happens at the activation function? The activation function is how information proceeds. It's how it changes at each. It's what really distinguishes the layers as distinct places, right?
Do you need to have the same activation function at every in every neuron of a given layer?
Yeah, every.
Okay.
I think generally speaking, it's a little more homogeneous in the sense that it's. I'm sure people have looked at it. I haven't looked at it.
Well, because if you have to have a consistent gradient descent, because at every point you're going to have to change the conditional gradient descent parameter. So if you don't have that change, then you're somehow going to have to figure out how to change where not to or where to also change your gradient descent. Because they're all conditional on.
So like the optimization function would vary according to not just the layer itself, but also.
Because they're all dependent on where you. Yeah.
Yeah.
Okay, so that's more of an architecture problem, not so much like an inherent fact of neural networks.
It's a good question, and that's a homework assignment for you.
I got a terrible. so we're like already out of time. I wasn't going to mention it, but
yeah, sorry.
No. You have all the time that everybody's.
We're almost done. There's only.
I've got all the time. Yeah. So go on.
Let's go to the charts. I know you guys got to go. So how do you find these hyperparameters? Like if you go look around the literature, you got to start somewhere. So what have other people done? I started with a genetic algorithm. If you've never coded up one of these things, it's worthwhile to do it. It's not that hard to do. It kind of it's a little bit, there's a little bit of a learning barrier to get your idea around this idea of a chromosome, the genes, and the analogies are what are confusing, but in its simplest terms, all you're doing is for every hyperparameter that you care about, you're creating a string of bits that would be long enough to capture the range of numbers that you want. So if you want to go, if your hyperparameter varies from plus 256 to minus 256, you have to have enough digits in this chromosome to accommodate that binary representation of that number. Okay? Now, the way it works is you represent a number in binary form, called a chromosome, and then you create, for every hyperparameter, the way I did it, there's multiple ways to do this. I created a tournament of contenders that started from a seed value, and then there were neighboring values produced through mutation, and so random bits were generated for numbers that created new numbers, and then these numbers were fed then into the network as real parameters of the network, and the network was then used k-fold cross-validation to calculate an error across the data. So if you can imagine, it's a very time-consuming process. And in the process of doing this, you can kind of get close to hyperparameters that are more optimal than others. And it's really, when you finally get to the bottom of the genetic optimization, you find that it's a form of random sampling that has a bit of momentum to it in the optimal direction.
So, and is this what actually ended up working for you?
This worked, but I found another method worked better, that I think is better to use in general. And it's called Bayes optimization.
Yeah.
So in Bayes optimization, remember, there's two main camps in statistics. There's frequentists, who are the hardcore, I'm taking data, and I'm going to base my bets on what I've, hardcore numbers, right? Roll the dice, I'm going to count up how many I get, and I'm going to base my odds on whatever I measure. That's a frequentist approach. Super valid, super useful. Bayesian statistics is more based on the idea that if I have any kind of prior information at all, I'm going to include that in my procedure, and I'm going to use that information to make my bet. And in the end, I'm not going to solve for an optimal parameter, one parameter value. I'm going to solve for a distribution over that parameter. It's a little bit abstract, but essentially that's called posterior. And when you dig into this stuff and just get to work with an exercise, it starts to make sense. By the way, whenever I am looking for code examples in art to find some place to start with, even out on Google or whatever, I never like to just copy someone's code and run it. I type it in myself. Unless it's some huge thing, which I'm never going to understand anyway, I won't even use it, right? I like simple things that I can get my head around. I type in every piece of code that I write. I don't go to GitHub and I use GitHub, but I don't use that code from someone. I don't do that because I don't understand it. To me, just running someone's code, maybe that's, by the way, though, if you do that, that's okay. If you learn that way, that's 100% correct. It's no better than, it's just as good as what I'm doing, okay? But for me personally, I just like to type in, when I'm typing things in code, copying an example and just trying to get something to work, I just prefer to type it myself because I'm thinking about stuff when I'm writing it. Now, obviously, you can't do that for a huge project. If you're under the gun, you have to get something working, some strange library, right? You can't do that like I do. But I just, when I'm typing stuff out, things occur to me. And these examples, when you're trying to figure these things out, things will occur to you, and they'll finally sink in. And that was true for me in this particular problem. So I learned all this stuff just by going through this problem, wanting to understand it, and doing little pieces at a time that were macroscopic. I know all this stuff sounds complex, but it's really not that hard once you just start somewhere and start typing, right? So my advice to you is just start typing, do something, and you'll learn it. All right, so I use Bayes and optimization. There are, turns out, some great tool sets that are free in Python. I use HyperOpt. You can pip install HyperOpt. And there's even one called HyperOps, which is a layer on top of HyperOpt. But I couldn't get that one to work to my level of, for the short time that I had. Maybe it's fantastic, but I ended up just using HyperOpt directly. And got pretty good success with it, but in the end, I think if you want to know the secret sauce, justice and the government secret sauce, I really think a random search is I think would produce the best results for this application, even though it's not application efficient. So there's a grid search, random search, Bayes search, genetic search. Everyone would tell you to use Bayes search, but I think a random search might actually help you come up with something that could perform a little better. But that's to be done.
Is that because Bayes search is sort of plotting? I mean, it's following like the most likely. You're more likely to hit a local minimum, basically, or maximum, basically, right? With a Bayes search.
I don't know. You're not supposed to be constrained by that, but you're asking the wrong person. I'm not an expert.
It's based on an empirical distribution, so basically it depends on where you start from.
It does.
So depending on where you start from, and
sensitivity
depends
on
on
the initial conditions.
And also to the data that you push into it.
Yeah,
right?
yeah, exactly.
Because there's a recency bias, and there's also wherever you start from.
Whereas
So you're
if
more
you
likely.
random search, you could be anywhere, but it requires a lot more horsepower.
Right. So this is why, like when you're drilling for oil, the most effective way to find oil is literally randomly, right?
Yeah.
This is an anti-fragile, right? Like
Right.
Nancy
So-
Nicholas' idea. It's always better to start.
So you're on. So you're on Oak Island, right? You guys
Oak
watch that
Island.
show? You watch that show? Oak
Uh-huh.
Island. The guys that are digging for treasure on the
Wait, are
island.
you a rocket scientist and you watch TV?
Oh my gosh! You gotta watch Oak Island, right? This is treasure hunting.
I was like so proud of myself. I'm so proud of myself going home, like under the TV, just blank wall, and I'm really like, this guy's over here watching TV.
I love Survivor.
While
I
we're
love
Hawaii
Survivor.
space.
My wife and I watch Survivor.
Everything you said is just.
I'm sorry.
I like that. Survivor Army.
We've watched that show from like season 1. It's been fun.
Okay.
Anyway, watch Oak Island. Those guys are digging for treasure, so you can get telling them.
They're just doing it randomly, right?
Huh?
Are they doing it randomly? That's what
They
works.
have
In drilling for oil, the best way to find oil is to drill randomly.
But I'll tell you one thing, with not even worrying about Bayes optimization or genetic optimization, if you just go, there's a lot of toy problems out there that you can kind of get started with just to understand what's like. There's this one guy, if you can remember one name that I'll mention before I leave tonight, there's a guy, and you guys probably already know about him, his name is Jason Brownlee. You go look up his tutorials on Google. He has like an amazing amount of stuff out there.
Brownlee.
Jason Brownlee. Look this guy up and just type machine learning Jason Brownlee. And he has a few books that he's selling that I think are great. I've bought every one. I think he's
spelled L-E-E.
Yeah, and it's a lot of really introductory examples of machine learning and how you do things. And he's really good, and it's a great resource. You look that guy up, and he has examples of grid search, random search, all kinds of stuff and the problems, the examples that he chooses are pretty good. They're interesting.
Did you go through the Paris examples?
He goes through a lot of Paris stuff, yeah. But this is a great resource if you guys want to look up.
Siraj.
So I'd love for you guys to just take away something that you can leverage from yourself in your own applications. And this guy Brownlee is doing some really cool educational stuff, and I like his articles. All right, so Bayes dropout. All right, so let's apply this to this problem. What happens? We do Bayes dropout optimizations. So what you're seeing on the x-axis are the Bayes optimizer is generating random samples. Okay, so and what you see on the y-axis is the fraction of dropout. If you multiply it by 100, it gives you percent. So when it starts off around 0, the range of values is pretty large. As the network, as the optimizer improves over time, it starts to narrow. So what this is saying is that it is using prior information as it learns sort of a limited range to choose for the dropout. And it's converging on more optimal value. So this is what the chart is indicating, it's supposed to show. So when you use a Bayes dropout procedure, it does indeed start to narrow in. And if you go look up the hyper-opt examples that I've talked about, you'll see examples where you can go construct, not from this application, but others. And you can see this kind of behavior. And there's a couple of really good examples out there that you can learn from. So this is dropout for the network. If you keep going, if you not only say, all right, I care about dropout, but I also care about maybe the activation function, or see what else did I optimize over.
Number of hidden layers, or
No, I didn't optimize as much over that because it was a much bigger computational. There's more to do. What I found was I just sort of did a couple manual hand tunings with the number of layers. And I found that a single layer for a multi-layer perceptron seemed to work as good as anything, honestly.
Yeah.
So it doesn't mean that there couldn't be more optimization, but that's what I found. So what I found was that in the bottom, so optimize over dropout and the activation in layer 1, which is the first hidden layer, and then the activation in the final layer, optimize over that. So I chose a set of about 5 different activations, and I let the network find the optimal ones using this Bayes procedure. And so this is what came back. And also, in the neural network, as you guys are aware, the form of initialization you give the network nodes for value starting prior to training is important. And that was discovered, there's been a lot of papers written about that. One of these papers is called by a guy named Xavier. It's called Xavier optimization. Xavier initialization. If you go look this up, it's really important. It turns out that if you optimize network nodes in a certain way, it has a big impact on the convergence of the training. It helps a lot. You can get to a much better answer quicker if you use these initializers. And there's also a Lacoon initializer that turns out to be one of the best ones that resulted from the optimization. And there's a lot of different initializers. In Keras, if you go look it up, the name for the Xavier optimizer is called a GlowRot uniform. That's what I use. That's why they call it GlowRot, but that's what it is. Go Google it, and you'll see the initializer. But if you go look up the guy's actual paper that was creative and found this and did the experiments, his name is Xavier. But it's kind of cool. What happened here was that there were 3 distinct families of architectures that emerged, and this came out of the hyperparameter optimization. The best one that I found corresponds to the choices that I have circled, and this is what I ended up using. So what are the final results? All right. So if you knew nothing and tried something just to kind of get something working, and you didn't know anything about what parameters to choose, if you had some big, large error and you were trying to find it, if you started with a multi-layer perceptron that had the naive architecture, and you just use the default values in Keras for the hyperparameters, okay? Just use default values or guesses. You'll get performance that really is not very good. And this is the mean RMS error, which is the standard deviation, okay? Which we just talked about. It's pretty large. However, if I do hyperparameter optimization, what I find is that the error goes from 205 nanometers plus or minus 60 to 44 nanometers plus or minus 25. Okay, so what that tells you is that the hyperparameter optimization in this naive architecture, even not being a very smart architecture, right? There's something that you would just start with. Improved by 365%. That's 2 orders of magnitude. That's big. That's a big improvement in performance. And not only that, I think one of the more significant things is that the uncertainty in those estimates was reduced by 140%. So that means that we're more, not only are we more accurate, but we're more confident in our estimates. Okay, by 2 orders of magnitude.
So, sorry.
No, yeah.
So there's a problem I often run into when I'm dealing with certain load numbers, and that's 100% of 1 is 2, right? Do you kind of like do a test against that premise in your mind? Because to me, like, obviously I don't understand optics at all, or I don't understand the significance of this, but not relatively, but absolutely, is this a big difference, or is it not a big difference? Does it mean a big difference only because of percentages, or is it a big difference in reality?
It depends on, in truth is, it depends on what matters in hardware performance of, say, a telescope. This is significant in that domain. Okay. This is a big deal in terms of how much it improves. Okay? And at the very end, I'll say, I only got 2 charts left, but at the very end, I'll say, well, 3 charts, but at the very end, I'll say a little more about this aspect to it and why this is not necessarily the best way to solve this problem with machine. Okay, I think there's some. I think what this does for us is it helps us think about the problem in a different way. It helps us understand even the way we usually solve it in a more general way. There's still really good applications here that we didn't have before. And I'll say more about that in a second. Sorry if I'm not really answering your question.
No, I think you are.
But there's more to say. Now, let's go to a convolutional network. So if we go to a convolutional network and look at the results, and again, the top row is out-of-sample data presented to the network that it had never seen for a given level of noise. It's not really that noisy. And the middle row are the images that the network would produce from its estimates of the coefficients, which you see in red compared to the ones in green.
And when you say that, you basically mean this is with the noise removed by that.
Well, there's some noise, but not enough to really worry about. I'm kind of looking at the ideal performance of the network.
Okay.
Yeah.
The only thing that's different between the last slide is that this is an improved model.
This is improved. It did 33% better. Okay. It
wasn't the last one.
Yeah. So look, the very first version was naive. We improved by 365%.
Just by changing the
just by tuning the hyperparameters. Okay. Now we throw out that model, the baby and the bathwater, and we jump to a convolutional network. Okay. And we've improved by 33% without really doing any careful optimization. So that tells me right away that this is probably a better starting point for something I really want to use. Okay? And the uncertainty decreased even further to 16 nanometers versus 25, which is a 60% improvement. So I'm 60% more confident in my estimates here also. Okay? And one of the cool things about machine learning and these problems is that because you're training the network and you're looking at sort of statistical performance across all your data, whenever you go to your manager, managers don't really care about the details. They just want to know what's the bottom line in terms of accuracy. How can they present to their higher up what you're doing, that their decisions were good to fund you to do this. They want to look good too, right? So this makes it easier to communicate your results because you're able to put error bars on your estimates. You're able to put error bars on your work because you have this huge statistical or a large data set, you hope, that you can then go back and say, this is my uncertainty. How can you report something that you're funded to launch without talking about uncertainty and the probability of failure? You have to know what those are. And with machine learning, because of the nature of the training, you kind of have that's an output it's a natural output of the process. To do it the old way, we have to do what's called Monte Carlo analysis and then go add the errors manually and then run a whole bunch of face retrievals the way we would used to do it,
Let's see if we get
and
that.
then put the error bars on the estimates that way. In this approach, it kind of falls out naturally, and I think that's one of the nice advantages to this analysis is that in machine learning, you have some statistical information readily available to you from your training data, usually.
As far as transparency, this is a problem I face too, is as far as transparency goes, whenever, whomever the final higher up is actually talking to the Congress, right? You get that error bar, but then they ask where they come from, and where do you get the trackability from all these new layers?
Well, you gotta do the work.
That's the problem. That's I find like that's the problem I have. Is like we can't use these things because the regulators won't allow it because they can't figure out what's going on in the middle.
They have to explain.
Yeah,
that's right.
You have to simplify it.
You do have. There is a lot of work.
So I'm trying to predict what you're trying to get at the end. Is I'm thinking you're using these as seed values for more, for methods that are more trackable, right? Is that what you're?
You mean the application of machine learning?
Yeah.
Oh, let's get to the last slide.
Yeah.
I'll tell you why I'm doing it. Why I think it's important for what we're doing. All right, so this is convolutional.
Do you know how well the convolutional neural network performed with the default hyperparameters?
See, what did I do for that case? I did do some manual tuning because there were a couple obvious things I wanted to play with. The initial hyperparameter run that I applied to the convolutional network didn't have the results that I expected. It was really gave me something back that wasn't doing as good as I thought it should do from just what I thought manually it should do. So I don't have like a really heroic result to report from hyperparameter tuning for the convolutional.
Okay. So I guess from your experience, what did you find performed or changed the accuracy more? Was it a change in the model from like a naive approach to a convolutional neural network, or just a change in hyperparameters?
It depends on which architecture. If you're using the multi-layer Perceptron naive architecture, the hyperparameter tuning that I applied in that case had a huge difference.
Okay.
The convolutional neural network, I really didn't get to complete the hyperparameter tuning for these results. I choose like some best guesses. My initial cut at hyperparameter optimization didn't really work as well as I thought it should, and so there wasn't really much to report. So this is kind of, I just thought this is a reasonable architecture to use, and I tried it, and it seemed to do pretty well. It competed well without much careful thought. Okay. So then, so with that said, what do you say? Tuning is important. You got to do it, right? At some level, you have to know something about either your problem or the parameters in the network. It's not surprising that you have to do this, right? Because we know already that the choices that we make in the network have an impact on what it predicts. True? So you might want to tune those things with the best performance that you can. It's kind of obvious, right? So it's important. Yeah. Reinforcement learning. I only got one chart on this. You guys already know about this. You had a speaker a little while back. I wanted to come to that. I wasn't able to get over. It was from John Hopkins.
Yeah.
Oh.
There was a guy from John Hopkins that came and talked about reinforcement.
The robotics guy.
Yeah.
Yeah.
I really wanted to come to that, but I couldn't make it to that one. But anyway.
Maybe we'll have him back if we're lucky.
Yeah, I'd like to meet him sometime. Was it good? You guys like?
I actually wasn't here for that. I was in Columbia. Were you here?
Yeah, well, it was good. I enjoyed it. It was interesting from the point of view of like what you're talking about. The biggest takeaway that you can get from this is he actually showed like a robotic model that was actually flying in a space that he was trying to train in. The whole problem was is that it's great that you could train the model to like pick up this, take it over to this, and drop it over on this with all the obstacles in room. The problem is that it wasn't generalized enough to actually, if you were to take that model into the wild, it would totally break down. And that's the problem, that what you're trying to do is try to get a model so that you have enough cumulative corpus knowledge to do something like that. But that's exactly what he threw up on the screen.
That guy is a PhD student candidate.
Oh, I mean, but
this guy's a pro.
Those guys.
No, but it's a different space. It's a totally different space to work in.
Yeah, this.
You weren't even here for that.
I know, but I want to defend the absent.
But just so you know, I think that you guys in school learning this stuff, you guys are just teaching me, man, right? You guys are the smart guys. I'm just don't do the motions. I like to learn. I like to talk to people. You always learn something talking to someone, right? That you didn't know before. I definitely value. I have fun. As many students as I can. We just try to do it because we always learn great stuff from students. We're funding a group at Rochester, and they're starting to do this stuff now, so I'm really excited about that. But reinforcement learning, I'm super stoked about this. This is really powerful stuff, guys. This is a different branch. It's not a neural network, right? It's the idea of the network is used in the reinforcement learner, but the whole idea of it's different, right? And I've gotten this to work. In this application, in the case you have, I know you guys have probably heard about this, but the idea of having an agent that is in the pursuit of something that is going to improve its quality of life in some way, right? Some kind of reward system is kind of the central idea here. And when you think about an agent existing in an environment and it operating in such a way to improve its state, and also in the environment, there could be some stochastic element, some random thing happening. It could be getting shot at, right? It could be on a battlefield, right? In those environments, solving for what is called policy. Policy is really what you're trying to find. Policy is going to be your recipe, your manual for what do I do next in this situation out in front of me, these stimuli around me. What am I going to do? That's what the reinforcement learning tries to solve, is that policy. And solving that problem is essentially called solving the Markov decision process. And that's the battlefield or the state that you're in with the stimuli that are coming in, and you're trying to do the best you can with it and improve your life or your family's life or your team's life or your reward or your telescope, whatever it is, you're trying to optimize your policy. This is a fantastic problem.
It does seem like the closest metaphor for our actual situation.
It does.
So you're using development.
Development equation. You guys saw development. These guys, this stuff was done way back in the 60s.
But they didn't have graphics.
Well, reinforcement learning. Well, you guys have seen the Atari demos, right? The games that the frames of the game images are the stimuli for the network.
Yeah, and
they essentially
goal
solve
function is the points, right?
Yeah. Well, this is why the neural network is so important in reinforcement learning, is because I mean, if you solve the toy problem, and so you guys have seen this, I'll show you. I got it on my desktop here, so I output it. If you solve the toy problem, this is an output from a Python program I wrote. Let me expand it just a little bit. This is the frozen lake problem, right? If you look into reinforcement learning, you're going to start somewhere. So what you see here is an agent in black. The black circle, the blue circles are holes, presumably in ice that the agent could fall into, right? And then the green is where the agent needs to be to get
optimal path
reward. Yeah. So what is, when you think about solving this problem, it seems sort of trivial in a way if you're not really understanding that there's a random element here. That every move that the agent can make exploring the environment, a random event can occur and throw the agent into a hole randomly after. And when the agent wasn't doing anything wrong, right? At no fault of its own, it can be tossed into one of these holes. It's called slippage in the ice. And when you train the agent in this environment, what you see, and I like to think of this as, I'll go ahead and just run it. It takes a little bit to run
It's supposed to be some idea of like pain versus reward.
Yeah, you can design the reward function engineering is what's important. There's a whole field that studies how you design the reward.
So what is his curiosity function here? Is he just randomly?
Yes. The agent is the Markov decision. The Markov decision process has been solved, and now we have policy. The agent is following the policy to try to get to the reward. Okay. Now you might ask, why doesn't the agent just go straight to the reward? Well, the truth is, it's because he's getting shot at.
Right. He doesn't know where he's getting shot.
Yeah.
Every time he moves, he's getting pain.
That's right. And if you turn off the possibility of the agent being tossed into a hole randomly, he'll go straight to the reward. Or she, doesn't matter. He'll go straight to the reward because it's not like they're getting shot at, right? They're just.
So in this sort of situation, the agent hasn't yet made the connection between there's a blue dot there. That blue
It has
dot-
made the connection. It knows that there's a good chance that due to no fault of its own, it's going to get shot at and thrown into a hole, say.
Wait, where?
So what will happen is
where are
that,
the shots coming from?
From the holes.
well, the holes. I'm just saying, like, I'm pretending it could be
Maybe
just
they're
as
like
easy.
But in reality, it only actually experiences any negative effect on its fitness value if it steps into a hole, right?
Well, you can design the function also to
Proximity severity, right?
yeah. You can also design the learning reinforcement learner to get a penalty for taking a long time to get to the hole, right?
Right.
You can also subtract from its reward that way. And what you find is that it kind of ends up with a different policy. It's a little faster. But if this agent could be randomly tossed into a hole, and if that penalty is large enough, you know what happens? The agent just sits still.
Right.
So
It doesn't trade.
So what's the reward function in this case?
Reward function, I go back and look at my code, but the reward is if it reaches the green, right? There's a maximum reward that it can receive.
Well,
But like in the,
every time
in
it
the
can move.
intermediary. what's
Yeah,
the-
I think there's a 0 reward if it just moves, but if it falls in the hole, it gets a negative.
Because
It's pretty simple.
all right. Do you have any more slides for us?
I think that's pretty much it. The last thing I'll just say for you guys, just to summarize all this stuff into one big chart for this application. Direct solve methods is the conventional way we do this. Overall, we can get better answers using direct solve than we can in machine learning. Okay? It's not too surprising when you think about this because we're really building a generalizer, a pattern matcher. If you have an equation that governs a phenomenon, and you know what that equation is, you probably should use that equation. It's exact. It's not a guess, right? Those types of systems you probably want to solve numerically the best of your ability. And that's what direct solve methods are. They will provide more accurate answers. But the reason this is important in this problem, and the reason I think we have an application for it, is because the machine learning can provide better starting points for the direct solve methods. See that? They can sort of get us out of those local minima and start it towards a global minima. And I think that's the real value of this. The other application is that with direct solve methods, we spend a lot of time doing parallel processing and making our Fourier transforms super fast using GPU cards and all this stuff, right? OpenCL, CUDA, and all this stuff. We do a lot of that work because it's important that we do it fast. I think machine learning has the potential to be fast once the training is completed and we have the weights. Once we have the weights, we look at matrix multiplies, which can be very fast. CUDA blocks, whatever. In our application, we have unlimited training data because we have models that we're generating data from. But the truth is, if our models suck, then our training is going to suck, and our output's going to suck. So the quality of our models is important. We don't have a free card because we have all this data. We got to still understand our Fourier optics and know how to generate the models properly. Yeah. The other thing is that we can solve for multiple things at once. I've only solved for the phase coefficients, but we can solve for multiple things in the optical system. Not enough time to talk about it, really, but we can. And then the hyperparameter tuning is pretty important. So anyway, I hope you guys, sorry this went for a long time, but I wanted to have a chance. To me, it's like a real treat to come out and get a chance to shoot down the conspiracy theories. Tell you guys what we're doing.
Lies. It's all lies.
Get a chance to. I hope you guys will stay in touch with me. Here's my email. I would love to be able to work with you guys if you have ideas. This is my personal email. So shoot me a line and tell me what you guys are doing because I'd like to learn more about what you guys are up to and your own applications and what you're doing here also. I think this is smart logic. I love hearing about companies, doing cool work, making the world a better place. Right?
Let's give it up for Dr.
You guys listen to me ramble for forever. I hope it was fun.
It was really fun and very informative. Thank you so much. Everybody, thank you for hanging in. I know that everybody is busy with the holiday season and living their lives. So appreciate everybody that's new, everybody that's been here before, everybody that made it out here. So thank you. I've got nothing else. We'll be meeting again later this month for a hack night. That's the third Thursday of the month. I don't think I'll actually be here, but someone will be here with pizza and beer, or at least pizza. And then starting next year, we will be doing every Thursday study hall and continue doing the first Thursday as a speaker lecture night. We're also happy to entertain like demos or lightning talks on hack nights, study hall nights, if anyone wants to practice their speaking chops. So that's all I've got. Thank you, guys.
Yeah, totally. Thank you guys.